Section 0 of Silent Sentinels. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Rick J. Silent Sentinels. Protective Relays for AC and DC Systems by Westinghouse Electric and Manufacturing Company. Silent Sentinels. Relays have been aptly termed Silent Sentinels, and they are Silent Sentinels. They stand on duty 24 hours a day, every day in the year, and year in and year out. They guard thousands of dollars worth of property and equipment. They prevent service interruptions and costly shutdowns. They are really and truly the Silent Sentinels of the electrical industry. Automatic control is a reality. Supervisory control has been introduced. The interconnection of systems is no longer an experiment. Service is now reliable and continuous. All of these are attributes of superpower, a new era in the electrical industry. And they were made possible through Westinghouse pioneering in the relay art. Not only has Westinghouse introduced most of the present-day relays, but this company has also developed various schemes and methods of relay application. Westinghouse relays and relay practice have played an important role in the progress of the electrical industry. It is the purpose of Westinghouse to maintain and extend this leadership to meet the exacting requirements of the future. End of Section 0. Chapter 1 of Silent Sentinels. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Rick J. Silent Sentinels. Protective Relays for AC and DC Systems by Westinghouse Electric and Manufacturing Company. The functions of relays. The protective relay is an electrical instrument, accurate in operation, sensitive in adjustment, and sturdy in construction, interposed between the main circuit or apparatus and the circuit breaker in such a way that any abnormality in the circuit acts on the relay. The relay, in turn, after proper discrimination as to the magnitude and character of the fault, causes the circuit breaker to function and relieve or protect the circuit or apparatus. The protective relay is used for three types of application: service protection, apparatus protection, and automatic control. Service protection. The most important duty of the protective relay is to protect the service against interruption. This may be done either by automatically sectionalizing the electrical system so as to disconnect the disabled section, or by automatically restoring the service after it has been accidentally interrupted. In large systems, the main lines are usually so arranged, either by means of parallel feeders or loop systems, that each substation on the main system has two or more circuits over which power may flow from the generating station. Thus, when a fault develops on one of the circuits, it may be disconnected without entirely cutting the substation off the system. In smaller systems, where small faults, which will clear themselves in a short time, are liable to occur, it is sometimes desirable to have a breaker reclosed after it has tripped out. In such a case, if the fault has cleared itself, the breaker will stay closed. But if after 2 or 3 reclosures the breaker continues to open, then the fault is permanent and the line should be temporarily cut out of service. Apparatus protection. Another use for protective relays is to protect apparatus, either by disconnecting it from service in case of failure or the occurrence of abnormal conditions, or by functioning to remedy wholly or partially the abnormal conditions. In cases where a short circuit or ground occurs in the winding of a machine, such as a generator or a transformer, it is usually necessary to have the apparatus disconnected. When the windings of a motor have become overheated on account of overload, a relay may be used to set in operation some device for reducing the load over a period of time, thus allowing the overheated condition to adjust itself. Automatic control. The recent phenomenal growth of automatic control has called for the development of a class of relays having mechanical and electrical characteristics similar to those of the protective relay, but whose function is to govern the automatic operation of the group of machines to which they are connected. These relays might be called control or discriminating relays, but because their structure is similar to protective relays, and also because they are primarily for the purpose of protecting or improving service, they are usually treated as protective devices. These relays are used for automatically starting and stopping substations and isolated hydroelectric stations, governing their loading conditions, and for other such work met within automatic control. The development of the relay art. Protective devices, more or less crude in their structure and operation, have been in use for many years. However, the exacting conditions of present-day practice demanded accurate and reliable devices, and these devices are the result of Westinghouse pioneer development. The first protective relay to be used was what is known as a fuse. This piece of apparatus was very reliable and included many of the characteristics of the present-day relay. It has by no means become obsolete, but as electrical systems began to grow, the cost of maintenance and replacement and the delay in restoration of service became a serious objection to the use of fuses on larger lines. This led to the development of the automatic switch, which was the forerunner of the present-day circuit breaker and served to disconnect a circuit upon the occurrence of any fault causing excessive overcurrent, low voltage, or some other abnormal condition. As systems became still larger and more complicated, and the demand for continuity of service became greater, it was found impossible to embody conveniently the discriminating features in the circuit breaker and still maintain the requisite sturdy structure. This led to the development of the present-day relay, which provides the automatic reasoning or thinking power of the circuit breaker. When, in 1902, the engineers of the Westinghouse Company were seeking a more accurate and reliable relay principle than the simple solenoid and core then in common use, it is natural that they should have turned to the induction watt-hour meter. This meter, another Westinghouse development, was already firmly entrenched as an example of simplicity, accuracy, and reliability among electrical measuring devices and lent itself readily to relay adaptation. So it happened that relay protection became at once a precise art, capable of fully responding to the advancing needs of the alternating current system. The first induction overload relay was brought out in 1902. In 1910, the improved overload and reverse current relay was produced. It was not until 1913, however, that the fullest advantage was taken of the inherent possibilities of the induction relay by combining it with a saturating transformer known as a torque compensator, a device developed by Westinghouse Company with the collaboration of Mr. F. E. Ricketts of Baltimore. It gave the relay a combination characteristic of both inverse and definite timing, an indispensable feature in selective operation. In 1914, the Type CO overcurrent relay was brought out, embodying improvements and combining in one case the induction relay and the torque compensator. In 1916, the Type CR reverse power relay was put on the market, combining in one case two induction elements, one an overload relay with torque compensator, and the other a selective watt element, preventing operation except on reverse power. Recently, the CZ impedance distance relay was perfected. This relay has a voltage element in addition to an overcurrent element like that used on the CO relay. It is intended for use on large, complicated transmission systems when sectionalizing by means of overcurrent and directional relays is often difficult and sometimes impossible. There are so many things to guard against in the protection of apparatus and transmission systems that many different types of relays have been perfected. Just the mention of the various types of relays manufactured today will give an indication of the various uses to which they may be applied. Overcurrent relays, directional relays, selective differential relays, impedance relays, temperature relays, reverse phase relays, voltage relays, power relays, polarity directional relays, transfer relays, long time limit relays, periodic reclosing relays, thermostatic relays, multiple contact relays, phase balance relays, short circuit selective relays, and service restoring relays. The Westinghouse Company not only introduced the designs of most of these relays, but also has developed methods of applying them. As a result of this pioneer work and the satisfactory operation of the relays, their use has grown enormously. Today, the necessity for their application is generally recognized. A good relay system is also a money saver because the damage caused when a fault occurs is reduced to a minimum by having the faulty part of the line immediately cut loose from the rest of the system. Another economic consideration is the smaller quantity of duplicate line equipment required to provide satisfactory service, or the increased load which can be carried on an existing system. Stated in other terms, the automatic sectionalizing of a transmission and distribution system allows all the copper to be used to its greatest possible advantage. All the operating companies have not taken advantage of the economies and improved service resulting from the use of relays. Others, who use relays to a limited extent, have, in no way, exhausted their possibilities. The rapid extension of transmission lines and the interconnection of power systems emphasizes the increasing importance of relay protection. End of Chapter 1. Chapter 2 of Silent Sentinels by Westinghouse Electric and Manufacturing Company. This LibriVox recording is in the public domain. Methods of applying relays to circuit breakers. Section 1. Alternating current circuit breakers. Automatic characteristics. Small alternating current circuit breakers often have automatic characteristics built into them, in which case relays are not required. These self-contained automatic characteristics are simple and usually consist of plain overcurrent trip coils arranged so that they can be adjusted to operate on any desired current value, a common range being 4 to 8 or 12 amperes. Sometimes, these trip coils are equipped with simple time limit devices such as dashpots, which are not very accurate, but which are reliable and, because of their simplicity, are in common use. Breakers so equipped are used without relays on small feeders where there is little need for the more highly developed discriminating action of the relay. Sometimes breakers are equipped with low voltage release coils, but from the consideration of continuity of service, this is not desirable because the circuit breakers so equipped will be tripped open whenever there is line trouble in the vicinity, even if the disabled line is automatically cleared from the rest of the system. Shunt tripping. Where automatic circuit breakers in themselves are not suitable, it is necessary to use relays. The simplest method of doing this is to place a direct current coil on the breaker and connect the protective relays so that their contacts will close the tripping circuit whenever it is desired to automatically open the breakers. This is known as shunt tripping. Most large circuit breakers are now electrically operated, and the trip coil to which the relays are connected is the same trip coil as that used during non-automatic operation of the breakers. Sometimes, however, the breaker is closed by hand and supplied with a trip coil for automatic opening. The question arises as to where to obtain power for tripping purposes. In the past, it has been common practice to use 6-volt storage batteries for this purpose, but trouble is often encountered with such a low voltage because of bad connections or poor contacts in the circuit. 12-volt batteries give less trouble of this sort and are often used, but it is recommended that 24-volt batteries be given preference. A large part of the expense of such an installation consists of the cost of the device necessary to keep the batteries charged, and, therefore, the extra expense of increasing the voltage from 6 volts to 24 volts is not a large percentage increase. Automobile batteries are probably the cheapest for this purpose. They can be obtained readily, but are said to have the disadvantage of losing their charge more rapidly than do some other types. Where the battery can be charged only at rare intervals, it is suggested that special batteries of the type used in railway signaling be installed. Sometimes, the battery can be arranged so that it will be kept charged by a trickle charge, and this practice is recommended. It is important to install a type of battery which will not freeze in severe weather, and it is important also to test each circuit occasionally to see that it is in working order. In most of the present-day generating stations and larger substations, a 125-volt direct current source is used for all control work. This source is usually maintained by a motor generator set, having a storage battery floating on the line in order to ensure against any possible interruption. Most standard circuit breakers can be equipped with trip coils for any of the mentioned voltages. Alternating current shunt tripping. Sometimes trip coils have been operated by alternating current voltage, But the trouble with such an arrangement is that their source of power is usually so closely associated with the circuits to be protected that in case of a heavy short circuit, the voltage will be too low to operate the trip coil, and thus the breaker will fail to open at the time when its proper operation is most necessary. Series tripping. A common method of tripping, known as series tripping, is to use the ordinary alternating current trip coil connected in series with the current transformer secondary, and to normally short-circuit this trip coil by means of contacts on the relay. When the relay operates, it opens these contacts and allows the current from the current transformers to flow through the trip coil and thus operate the breaker. There are several objections to this method, one of them being that some protective relays are intended to operate when the current flowing through the trip coil is comparatively small and, therefore, insufficient to operate the breaker. Another objection to this arrangement is that heavy contacts are required, and it is difficult to apply these contacts to relays having the accuracy required of present-day service, and having the other necessary requirements, such as a small burden on the current transformers. It is usually demanded that the trip coil shall be capable of operating when the current is at least as low as 5 amperes, which requires that it shall have an impedance of 1 ohm or more. On the other hand, a short circuit may be so heavy that the current in the trip coil is limited only by the ability of the current transformer to supply it. Such short circuit values through the trip coil may amount to 100 or 200 or even 300 amperes. It is, therefore, necessary for the relay contacts to be able to carry 5 amperes continuously without overheating, and at the same time be able to successfully withstand the opening of a circuit of approximately 300 amperes at 300 volts. Needless to say, no satisfactory relay has yet been designed for this service. Where conditions are such that tripping by means of the current transformers is demanded, the Type BT transfer relay can be used, provided reasonable attention is given to keeping its contacts in proper operating condition. Certain types of circuit breakers are furnished with a direct trip attachment, an excellent device even though the name is somewhat misleading. Such breakers are tripped by current from the current transformers, but the arrangement is such that sensitive relays can easily control the operation of the trip coils without injury to their contacts. This direct trip attachment operates on the same principle as does the Type BT transfer relay, which is itself described farther on in this book. Section 2. Direct current circuit breakers. Direct current circuit breakers usually have automatic features included in their structure. Overload trip coils are customary, and often they are equipped with inverse time limit devices. Underload release coils have been used in a few rare cases, and low voltage release coils are quite common. Where relays are used to open direct current breakers, the conditions are sometimes such that tripping can be done by the low voltage release coil. This can be effected either by connecting the relay contacts in series with the voltage release coil so that the relay opens the circuit, or by connecting the relay contacts around the trip coil so that they short-circuit it when the relay operates. When the contacts short-circuit the low-voltage release, it is necessary to use a resistance in series with the coil so that when the relay short-circuits the coil, it does not short-circuit the line. This same method can also be applied to any alternating current circuit breaker equipped with a low-voltage release coil. Another method of opening a direct current breaker is by means of a shunt trip coil, deriving its power from the direct current bus bars. Usually, such breakers are hand-operated, but occasionally they are electrically operated. The recent increase in the use of automatic control equipment has called for new designs in circuit breakers that are both opened and closed electrically. These are particularly useful on service restoring equipment or, as they are sometimes called, automatic reclosing relays. Section 3. Control circuits. Circuit opening versus circuit closing tripping. Occasionally the question arises as to the relative merits of circuit opening and circuit closing methods of connecting relays into the circuit. However, when a separate tripping circuit is used, it is the universal practice to use circuit closing relays to protect against short circuits. It is true that the method of control used in industrial work, particularly elevator control, makes use of circuits that are normally closed so that any failure in the circuit will shut down the apparatus. However, when the service is to be protected, as distinguished from the apparatus,
it is considered the better policy to use control circuits which are normally de-energized. In the case of automatic operation of stations, the question is largely one of convenience, and both methods are used. Supervision of control circuit. Closely allied with this question is the one of supervising the control circuit so that the operator can be certain that the circuit is always in an operative condition. This supervision can easily be accomplished by use of a supervisory lamp, which is connected in the control circuit in such a way that a small current continuously flows through it and through the entire tripping circuit, including the trip coil. In case of failure anywhere in the tripping circuit, the lamp will, of course, be extinguished. The control circuit can be so arranged that the red indicating lamp, which normally indicates the circuit breaker is closed, will also supervise the tripping circuit. Trip-free breaker control. Hand-operated, automatic circuit breakers for both alternating current and direct current are almost invariably full automatic. That is, the operator cannot hold them closed on a short circuit. When a circuit breaker is operated by protective relays, it is usually considered desirable to retain this characteristic, and, therefore, it is customary to use what is known as a trip-free auxiliary relay in the control circuit, so that if the operator closes the breaker on a short circuit and the relay trips it open, it will not reclose, no matter how long the control switch may be held in the closing position. The trip-free relay locks out the closing circuit until the control switch is released. Multiple control circuits. Sometimes it is desirable to trip several breakers simultaneously from one relay. This can be done by connecting their trip coils permanently together, but it is objectionable when it is also desired to operate them independently by hand. The usual requirements are to have the circuit breakers operate independently under normal conditions and operate simultaneously only by the relays. It is, therefore, necessary to keep the trip coils separated when they are to be manipulated by hand. One way of accomplishing this is to interpose an auxiliary multi-contact relay between the protective relay and the group of circuit breakers. This is sometimes considered objectionable because it introduces another piece of apparatus into the protective scheme. Another method of accomplishing the same result, where it is desired to operate only two breakers simultaneously, is to use protective relays equipped with double contacts. These contacts are arranged to keep the two tripping circuits separate and to close them simultaneously. Another method quite commonly used is to arrange the tripping circuits so that normally all of the trip coils are connected together so that a single relay can trip all the breakers. A special contact on the control switches is so arranged that whenever one of the breakers is operated by hand, the special contact on the control switch will first break the tie between the various circuits. Time required to open a breaker. Where a time limit is depended on to discriminate between various relays, it is important to consider the time required for the operation of the circuit breakers themselves. Although the size of the circuit breaker has much to do with its speed of operation, its mechanical adjustment is also of importance. Much of the time required for operation is consumed in energizing the trip coil and in overcoming the inertia of the moving parts, so that after the contacts have once separated, the time required for the breaker to complete its travel is not long. Small circuit breakers, equipped with instantaneous automatic overcurrent trip coils, can be made to operate very rapidly, because upon the occurrence of a short circuit, the trip coils will release the latch quickly, sometimes within a cycle. The characteristic curves, Figure 7, show the time required to open several modern types of circuit breakers. Signals. An audible signal of some kind is usually provided to sound whenever a breaker is tripped automatically. A common method of accomplishing this is to provide a separate bell bus on one side of the control circuit and interpose a series signal relay between the bus and the source of supply. The normal hand operation of the breakers is done from the main control bus, so that no alarm is given, but whenever a primary relay operates, it energizes the bell bus and the signal relay. The operation of the signal relay usually causes a bell to ring continuously until the relay is tripped. A type OL relay, which can be manually reset by a pull button on the relay cover, is recommended for this purpose. If the signal relay is to be mounted in the rear of the panel, the type OX should be used. This type is electrically reset by means of a push button conveniently located on the front of the panel. The objection often arises that this relay scheme interposes an additional hazard in the tripping circuit, although its operating coil is wound with wire of such size that it is not liable to become accidentally open-circuited. Because of this objection, it is becoming the common practice to use an alarm relaying having a shunt coil operated in parallel with the trip coil of the circuit breaker. In order that one signal relay may be operated by any number of protected relays, it is necessary to have a separate signal contact on the protective relay, as shown in the diagram, Figure 8. End of Chapter 2. Chapter 3, Part 1 of Silent Sentinels by Westinghouse Electric and Manufacturing Company. This LibriVox recording is in the public domain. Alternating current systems. Section 1. General theories of line troubles. Alternating current systems suffer from more severe short circuits than do direct current systems, primarily because of their better inherent regulation, and often because of the greater power concentration. Modern polyphase systems have become so large and complicated that they present many difficult problems, due to the various unbalanced faults which can occur. Alternating current transmission systems may be divided into two general classes. First, those having the neutral insulated from ground. Second, those having the neutral connected to ground metallically. The second classification may be further subdivided into four groups, known respectively as solidly grounded neutral systems, low resistance grounded neutral systems, medium resistance grounded neutral systems, and high resistance grounded neutral systems. The solidly grounded neutral system is one having its neutral connected metallically to ground without any limiting resistance in the circuit. The terms low resistance, medium resistance, and high resistance refer to the relative values of limiting resistance inserted in the neutral connection between the neutral point of the system and ground, and are dependent on the neutral voltage of the system under consideration. As a general rule, a system may be considered as low resistance grounded neutral if the grounding resistor is of such a value as to produce in any circuit, for a fault to ground, a current which, under minimum generating capacity conditions, is at least 4 times the line relay current setting. A medium resistance grounded neutral system has a grounding resistor of such a value as to limit the current for a fault to ground to less than 4 times the current setting. For the line relays of that circuit. This fault current will still, however, be greater than the maximum load current over the feeder, even under abnormal operating conditions. A high resistance grounded neutral system has its grounding resistor of such a value that the current for a fault to ground is on the order of full load current of the grounding transformer bank or less. Protection for faults from wires to ground may or may not be possible, depending on certain local conditions which will be discussed under Methods of Clearing Ground Faults. Solidly grounded systems. Systems having their neutral solidly grounded are subject to short circuits between one wire and ground whenever that wire becomes accidentally grounded. They can also suffer from short circuits between only 2 wires of the system, as well as between 2 wires and ground. In addition to these unbalanced short circuits, such a system can suffer from a balanced 3-phase short circuit. In considering a system which has its neutral grounded, it is customary to assume that the ground resistance between the neutral and the fault is comparatively low, so that it does not decrease the value of the short circuit current by any great amount. However, in some localities the ground resistance may be high, but such conditions are not of common occurrence. In calculating the quantity of ground current likely to flow, it is important to bear in mind that the impedance of the circuit is high, because of the great separation between the line wire and the path through the ground. Ungrounded systems. On systems having an isolated neutral, the 3-wire short circuit and 2-wire short circuit are the same as on grounded systems, but an accidental ground does not produce a short circuit as it does in the solidly grounded system. If the system is small, an accidental ground will make little disturbance, or at least it will not cause any abnormal value of current to flow. But if the system is large in extent, so that the electrostatic capacity between conductors and ground is high, a noticeable charging current will flow into the fault. On a large system, there is always a charging current flowing in the conductors, but such a charging current is normally balanced and is distributed throughout the network. When an accidental ground occurs on one wire, the potential between each of the other two conductors and ground throughout the system is increased beyond its normal value by the factor 1.73, and these wires, therefore, require a greater charging current than that which they normally carry. As shown in Figure 10, each of these wires represents the plate of a condenser, the ground being the other plate, and the wire leading to the fault represents the connection between the source of potential and the ground plate. Therefore, this grounded wire must carry all the charging current for the two condensers. The value of this current is difficult to calculate accurately, but an approximate value can be very easily obtained, and it is about twice the normal charging current of the system. The normal charging current can be calculated from tables which take into account the size and spacing of the conductors and the frequency of the circuit. Reason for grounding through resistance. If an ungrounded system is small, with a consequently small charging current, it is possible to operate the system when one of the conductors is accidentally grounded, so that the necessity for cutting out the disabled section is not urgent. Furthermore, most grounds are usually of a temporary nature, such as a flashover on an insulator, and they will clear themselves without damage. If the system is large, these disturbances will become more frequent and the charging current will increase due to the greater electrostatic capacity of the system, to such a value that an arc over the insulator will not break, but will continue until serious damage has been done and until the line probably is burnt down. Therefore, on large systems, it is necessary to provide some means of cutting out a disabled section, and this, usually, requires some method of grounding the neutral. Grounding is also necessary in order to relieve strains on insulators because, as has been shown, when one line is accidentally grounded in an ungrounded system, the voltage between the other two lines and the ground is increased 1.73 times. The solidly grounded neutral has been considered, and it was shown that an accidental ground on a conductor results in a short circuit. This causes considerable disturbance, which is frequently so severe that some of the load, particularly synchronous motors, will be forced to drop off the system before the fault can be cleared. This disadvantage may be overcome by inserting sufficient resistance in the neutral connection to limit the current to a small value so that an accidental ground will not seriously disturb the load. Sometimes this resistance is so low that the ground current approaches a short circuit in magnitude and can therefore be handled by ordinary relays intended for short circuit protection. But it is becoming a common practice to use a resistance of such magnitude that the ground current is kept below the full load value of the current in any of the feeders. This is particularly useful in cable systems because cable faults usually start between one conductor and the grounded lead sheath, and as the ground current is held to a small value, it is possible, by means of suitable relays, to disconnect the faulty cable before the trouble has developed into a short circuit, with a consequent interruption to the nearby load. Nature of open wire short circuits. The nature of a short circuit and its effect upon relay operation have been determined both by experiment and years of experience. On overhead lines, short circuits are usually arcs, and the resistance across them is small and of a fairly stable value. Short circuits of this nature sometimes cause extensive trouble wherever there are several transmission lines on the same structure due to the blowing of the arc from one circuit to the adjacent ones. Flashovers caused by lightning are a particular annoyance because the lightning usually strikes on the windward side of the structure, the lightning coming with the storm, and the wind then may blow the arc across all the other circuits. For this reason, it is advantageous, if possible, to disconnect the first line in trouble before the arc has had time to involve the neighboring lines, but this is always difficult and usually impossible to accomplish. Several cases are known where trouble has communicated itself in this manner to several parallel circuits, each of which was equipped with practically instantaneous relays, and yet the circuit breakers could not open fast enough to clear one line before the arc had blown across to the other lines. In checking some of these faults, the Weather Bureau records were consulted, and it was found that the average wind velocity at that station was about 4 miles per hour, which corresponds to approximately 6 feet per second. When it is considered that an arc has no inertia, it is easy to see why trouble on one circuit will involve the neighboring circuit even on a quiet day. It sometimes happens that in testing lines after an extensive interruption, the switchboard operator closes in the good lines first and then closes in the bad line. thus starting trouble which involves all the lines and trips them out again. Therefore, in testing circuits, it is good policy to vary the sequence of closing the breakers after one sequence of operation has failed to hold. On systems having a large connected generating capacity, the length to which an arc can be drawn out by the wind is almost unbelievable. Arcs more than 20 feet long within a station have been seen, and authentic cases are recorded of arcs having a length of 200 feet or more on high voltage lines. These long arcs usually occur on lines of 66,000 volts or above, but where towers are used to support the structure, it is surprising how seldom they jump from one circuit to another. This is probably because the grounded steel tower acts as a shield between the circuits at the point where the trouble starts, namely, at the insulators. Nature of trouble in cables. Because trouble in cables usually occurs at the joint in manholes where there is danger of injuring adjacent cables, it is essential that the defective section be disconnected within a reasonable time. Tests have been made on an 11,000 volt system, which proved that the voltage across the arc between the two conductors amounts to 2 or 3% of normal voltage, the value being practically independent of the current. This is easily explained if we assume that the resistance of the arc decreases as the current through it is increased. These tests were made by sawing off the cable and allowing the arc to form between the conductors at its end. It is not only possible, but also probable, that when the arc is confined in the cable its resistance will increase as the pressure increases due to the generated gases, and this, naturally, will increase the voltage across the arc. This voltage will ensure the correct operation of directional relays, even when a fault occurs close to the switching station. Most faults start as a ground between one conductor and the lead sheath, usually due to the entrance of moisture into the cable. By means of a suitable relay installation, it is often possible to disconnect any of these faulty cables before the arc has involved the other two conductors. One operating company has found, by an analysis of defective sections of the cable, that about 50% of the cable troubles are cleared without developing short circuits. Power factor of short circuits. It is the general impression that short circuits are of low power factor, but this is usually not so. It is true, of course, that the total reactance of the circuit involved in the short circuit is high compared to the resistance, but most of this reactance is in the apparatus, and is not usually of importance in relay work. We are interested usually in the power factor of the line itself during times of short circuit, and this, of course, depends on the relative resistance and reactance of the line conductor and is, therefore, independent of its length. High voltage 60-cycle overhead transmission lines sometimes have a power factor of less than 50%, but that is not the rule, and 25-cycle lines and all cable circuits have a much higher power factor. It should be remembered, however, that the power factor of a short circuit or ground fault may vary widely according to conditions, and this fact should always receive consideration when applying relays, especially those dependent for their operation upon both voltage and current. Distortion of phases. In faults involving all three wires of a three-phase system, the only abnormal conditions which ordinarily will exist are the excess flow of current into the fault and the low voltage in its vicinity, but these present no difficulties in relay protection. Any other fault which may occur, such as a two-wire short circuit or a ground on one or two wires, three-wire, three-phase system considered, will not only cause an abnormal current flow, but will also necessarily result in an unbalanced or distorted condition of phases, on account of the abnormal current flow being in only one or two of the three lines. This distortion is greatest in the vicinity of the fault, and gradually lessens as the distance from the fault increases. Exact conditions existing after a short circuit or ground has occurred are hard to determine because so many conditions and characteristics are present in every system, which vary widely in different systems. Some few years ago, Mr. G.H. Gray and Mr. L.N. Crichton made extensive tests respecting such conditions, using an artificial transmission line for the purpose. Figures 12, 13, 14, 15, 16, and 17 show some of the results of these tests plotted vectorially. The values plotted were taken from oscillograms and thus represent actual conditions existing after the fault occurred. Effect of phase distortion on relay operation. Phase distortion has no effect on the operation of straight overcurrent relays. In the case of directional relays, however, where the correct operation of the relay is dependent on the operation of a wattmeter element, phase distortion must be considered. A true wattmeter will reverse if the angle between the current and the applied voltage becomes greater than 90 degrees. Therefore, the problem in the application of directional relays is to make the voltage and current phase relations such that the worst conditions of phase distortion will never cause the angle between the current and the voltage to exceed 90 degrees. The vector diagrams, figures 18 and 19, show the conditions which may exist. In figure 18, the current and voltage vectors of only one phase are shown. AO represents the voltage from A to neutral, and I sub 1 represents the current in leg A with a slightly lagging power factor. Figure 19 shows a possible distortion of phases when a short circuit occurs from line A to C. A short circuit of unity power factor would mean a heavy current in phase with voltage AC, but due to the reactance of the circuit, the current would probably lag considerably more and would take a direction as shown by the vector I sub 2. AO, the voltage to neutral, changes its direction only slightly and, as is evident, the angle between AO and I sub 2 may easily be greater than 90 degrees. Now, if a directional relay with a wattmeter winding has its voltage coil connected to AO and its current coil to phase A, it will tend to reverse as soon as the angle OAI exceeds 90 degrees. It will thus close its contacts and trip the circuit breaker with current flowing in the normal direction, opposite to that for which the relay is supposed to trip. Actual tests have shown that the angle OAI sub 2 may be as great as 120 degrees with a short circuit between A and C. This will cause directional relays to close their contacts on normal direction of power flow when the directional contacts should be held positively open. The most satisfactory solution of this problem is to connect the potential coil of the relay to a voltage which is 30 degrees behind the current at 100% power factor. Referring to figures 18 and 19, if the voltage were taken from phase A to C, then under short circuit conditions, the angle CAI always would be less than 90 degrees, and the directional relay contacts would never close on normal direction of power flow. Phase relations with delta star connected transformers. Where directional relays are to be applied at substations having delta star connected power transformers, it is often desirable to connect the voltage transformers on the low voltage side, while it is necessary to have the current transformers connected in the high voltage leads in order to get the true current flowing. Special care is necessary in such cases in order to secure the connections which will give the proper phase relations between the voltage and current for the relay. As already stated, in order to assure proper operation of the relay with the phase distortion accompanying a short circuit or ground, the relay current should lead the relay voltage by 30 degrees under normal conditions, with a 100% power factor on the system. Figures 20, 21, 22, and 23 show the correct connections for such combinations to be used in applying type CR directional relays. The vectors show the relative phase relations for each step of the transformation. Section 2. Methods of clearing short circuits. The simplest system of distribution is one having a single source of power with a number of feeders leaving the generator bus bar, each feeder, in turn, being subdivided into a number of small feeders. This is termed the radial distribution system. The protection of such a system against short circuit may be secured by overcurrent protective devices. The smaller branches may be disconnected automatically from the remainder of the system by the blowing of a fuse or the operation of instantaneous circuit breakers. The circuit breakers near the generator should be equipped with definite time relays. A time interval between the successive relays, long enough to assure a reasonable margin of safety above that required for the circuit breaker to operate, is allowed. Relays at the generator bus are given the highest time settings. The settings of the other relays are decreased as their distance away from the generator increases until the most remote relay has an instantaneous setting. Figure 24 shows a typical radial system. The smallest branches, such as those leading out from substations C and D, may be sufficiently protected by fuses, while other remote feeders, carrying greater power, may require a circuit breaker which may be equipped with an overcurrent trip coil so that the breaker will be open almost instantly upon the occurrence of a short circuit on the feeder. As we proceed back towards the generating station A, overcurrent relays, such as the CO relays, are necessary in conjunction with the circuit breakers to give a definite time for tripping. Assuming that there is a short circuit at M, the excess current will flow through relays numbers 1 and 4, but number 4 will trip in 1 second, thus cutting off the short-circuited line before number 1 has had time to trip. Likewise, with a fault at N, both relay numbers 2 and 5 will be affected, but number 5 will trip its breaker first. It is common practice to allow approximately 0.5 seconds between the successive relays and 2.0 seconds as the maximum permissible setting. In addition to securing discrimination on the part of the relays by means of a definite time feature, it is also possible to discriminate by the current setting, because trouble which occurs at the far end of one of the branch lines will not draw so heavy a current as if it were near the generating station. Relays, such as number 7 and 8, figure 24, on the remote lines may, therefore, be given a setting which will cause them to operate on a much lower current than will the relays near the generator. The Westinghouse CO relay is especially adapted for such installations because it combines the inverse and definite minimum time characteristics, and because it also may be set to operate on various values of current. In radial systems, in which the number of branches becomes so great that it is difficult to allow the necessary time setting between successive relays without making the time setting on the relays at the generating station extremely high, the CZ distance or impedance relay may be used instead of the CO relay. When this relay is used, the relay nearest the fault operates the quickest, thus making time settings unnecessary. This type of relay is slightly more expensive than the CO and requires voltage connections in addition to the current connections. The ring or loop system. The ring or loop system, as indicated by the name, is simply a continuous transmission line running through a series of substations and finally terminating at its starting point. This forms one of the best ways of securing uninterrupted service with a minimum expense for feeders. The number of substations which may be thus tied together depends upon the geographical location and the relay protection that is desired. Where the CO and CR relays are used, the number of stations is limited, due to the fact that the required time intervals necessary between successive relays add up to an unsafe value. With the advent of the CZ relay, however, this difficulty is largely removed. On a simple loop system having only one source of power, directional overcurrent relays, with definite time limit characteristics, may be used for protection against short circuits. The time setting of each successive relay must be increased by an amount sufficient, usually 0.5 seconds in practice, to allow time for the circuit breaker in the preceding substation to open. The directional relays applied at each substation are fixed so that they will trip only when excess current is flowing away from the substation bus. It is, therefore, evident that with successive time settings, the relays at each end of any faulty section will be the first to operate, serving to isolate this section of the loop. Straight overcurrent relays may be used at the generating station or source of power, as any fault on the system can cause power flow in only one direction from this point. Figure 26 shows a typical loop system tying in 4 substations with the generating station. It shows the application of directional overcurrent relays on each side of the substations and straight overcurrent relays at the generating station. The arrows indicate the direction in which the overcurrent must flow to trip the relay, and the figures show the definite minimum time setting of the relay. Considering a fault at M, current will flow to it from substations B and C. The 0.6 second relay will trip out the substation C end, and the 1.6 second relay at the substation B end. It should be noted that the same fault current flows through the 1.1 second relay at substation D in the proper direction, and the 1.6 second relay at E. The relay at C, however, trips first, clearing the fault. This same current flows through the 0.6 second relay at D and the 0.1 second relay at E, but in the wrong direction to cause them to close their contacts. A fault at any point may be similarly checked out. Where a loop system has more than one source of power, the application of relays becomes somewhat more complicated. The same type of relay may be applied with the same system of successive time settings. One difficulty that is encountered in such a system is that if the relays are set for a condition with both sources of power connected, Such settings must be changed somewhat when one source of power is disconnected. In this case, the entire relay system has to be readjusted. This illustrates the necessity for using relays whose adjustment can be changed quickly. Type CO and CR relays. The Westinghouse CO and CR relays are specially adaptable for use on loop systems, as they embody the definite time limit characteristics with a very flexible adjustment for values of operating current. In addition to the dependable accuracy of the relay settings and the speed of action, any necessary changes in the settings or adjustments may be made quickly and conveniently. Type CZ impedance relay. Sometimes, it is very difficult to arrive at a suitable method of protection for a loop system due to the fact that, when applying the standard time element relay and allowing the necessary time intervals, in order to secure selectivity, the time settings of the relays at the ends of the loop become necessarily higher than is either safe or advisable. A more recent and flexible relay application for such complicated systems is the use of the impedance or distance relay developed by the Westinghouse company. With the proper application of the CZ relay, all time settings are taken care of automatically after each relay has been set to protect its own section of the line. Each relay is set to trip out its own section of the line in a time corresponding to the distance to the fault, the maximum time required being 0.75 seconds, which corresponds to a short at the far end of the line. Regardless of on what section of the system the fault takes place, the proper relay will trip out, and at no time will the isolation of the faulty line require more than 0.75 to 1 second to accomplish. The other CZ relays on other sections of the line will start to function, but by reason of their greater distance from the fault, they will not trip out their breakers, but will return to their normal position as soon as the relays on the faulty line have isolated the fault. This automatic increase in timing with increase in distance to the fault is the unique feature of a CZ installation. With the addition of a directional element to the relay main element, this relay may be applied on loop systems in the same way as CO and CR relays. The choice between the use of the two applications is dependent mainly on the cost. The CO-CR application is preferable whenever it can be supplied satisfactorily, inasmuch as the relays themselves are less expensive and the CO relays do not require a voltage connection. Where the system is complicated and the sections of sufficient length, long enough to give approximately 3% voltage drop between ends of the section, the CZ relay is applicable and should be used. This voltage, which is a measure of the impedance voltage drop to the point of short circuit, is supplied to the voltage element of the relay by potential transformers connected either to the high or the low side of the power transformers. If connected to the high side of the power transformers, the potential transformers will supply to the relay elements voltages corresponding exactly to the line voltage, and accordingly the relays will function properly. In case only potential transformers connected to the low side of the power transformers are available, it sometimes becomes necessary to use voltage compensators, similar to those used with voltage regulators, to compensate for the drop through the transformer which has been inserted between the relay and the line to be protected. Compensators are provided, 1. To compensate for the impedance drop in the power transformer, which drop is present when short circuit current is flowing through the transformer into the line that is shorted. 2. To compensate for the shift in the neutral at the ungrounded substation end of a solidly grounded system, which shift occurs in case of an accidental ground on the high side. Figures 27, 28, and 29 show typical CZ applications with and without compensation, as required. Protection of parallel feeders. Where two or more identical or similar lines connect a generating station and a substation, two substations or two generator stations, they are termed parallel feeders. Such an arrangement of feeders may be applied to either radial systems or loop systems, and it has come into very common use due not only to the fact that it is an economical and convenient means of increasing transmission capacity, but also to the fact that it forms a most flexible system for economical operation of lines and lends itself very readily to relay protection. CO and CR relay scheme. In general, the standard application of CO overcurrent and CR directional overcurrent relays may be applied to parallel feeders in the same way as in the case of single lines of loop systems. Where the system is large, however, the time settings on some of the relays must necessarily be high in order to secure selectivity, and this in itself is often a difficulty which cannot be overcome. Balanced power scheme. A general solution of this problem is to use a balanced system of relays. Separate parallel circuits, which normally carry equal currents, are balanced against one another. If the currents maintain their equality in spite of their magnitude, it is a good indication that no fault exists in that particular group. On the other hand, a certain degree of unbalancing would be a safe indication of trouble. The problem, therefore, is, in general, to separate a current which is representative of the actual unbalancing and pass it through proper relays so that the faulty feeder may be disconnected. One method of solving this problem is by balancing the current flowing in the two feeders by the cross-connection of directional relays. This scheme may be applied to any system, no matter how complex, if its feeders are run parallel between the switching points. The relays may be set to act almost instantaneously. With this system, the relays can be set to operate on currents smaller than the full load value of each feeder. This arrangement enables the clearing of trouble on a system having the neutral grounded through a high resistance, when the total trouble and load current flowing through a single cable may be less than the maximum load current of that cable. The schematic diagram, Figure 32, shows the scheme of cross-connection of directional relays applied to a system of 4 parallel feeders. Figure 33 shows a complete diagram of standard connections for a pair of 3-phase feeders, except that the tripping circuit is omitted. By reference to these two figures, it will be seen that all the current transformers in the generating station are connected in series. Likewise, those in the substation. Each relay is a unidirectional relay and is shunted across its own current transformer. Under normal conditions, the load in each of the cables will be the same, and since the relays are of a higher impedance than the current transformers, the current from the latter will circulate through all of the transformers in series without any flowing through the relays. If the trouble occurs at any point outside the section protected by these cross-connected relays, the current through the protected lines will still be balanced, and consequently there will be no unbalanced current tending to operate the relays. On the other hand, if trouble occurs on a line within the section, the current through the defective cable will be higher than that in the other, and the excess current from its current transformer must, therefore, pass through the relays. While the system is in this unbalanced condition, current will flow through all the relays, but in the proper direction to cause only the relay at each end of the defective cable to act. Figure 33 shows auxiliary pallet switches connected in the transformer secondary circuit. These switches are also connected mechanically to the operating mechanism of the breaker so that, when the breaker opens, the current transformers on the feeder will be short-circuited. By this method, a line can be cut out of service without interfering with the electrical balance in the remaining transformer circuit. However, these pallet switches are not needed in the transformer circuits except where low-ratio bushing-type current transformers are used. Ordinarily, the impedance of the current transformer secondaries is sufficient, when the primaries are open-circuited, to prevent any appreciable current from passing through them. By referring to figures 32 and 33, it will be observed that under balanced conditions, no current is flowing in the relay current coil. When a fault develops on one line, the current and voltage in that group of relays are in such a relation as to close the directional element contacts, while in the other group of relays the voltage is in the opposite direction and so opens the directional element contacts. It is therefore apparent that if the directional element were made double throw, one set of relays could be made to protect two parallel feeders by cross-connecting the current transformers. Such a relay is available under the name of the duodirectional type CR relay. Its chief disadvantage is that either abnormal phase distortion or mechanical vibration may displace the relatively light directional element and trip the circuit breaker before the fault has been isolated, thereby interrupting service over the good line. A further adaptation of the cross-connected CR relay protective scheme gives both short-time, low-current protection when two feeders are operating in parallel, and long-time directional overcurrent protection when one of the feeders is operating singly as a part of a transmission loop. Figure 34 shows the complete connections for two incoming feeders to a substation. The voltage and current connections to the relays are so made that the relays of each set close their directional element contacts when unbalanced power is flowing out over the line which those relays protect. Each relay is provided with a tap between the directional element contacts and the overcurrent element contacts, and these taps are joined to a common bus for each pair of lines, so that any overcurrent element can trip either circuit breaker by acting through the directional element contacts of the corresponding relays. With the feeders carrying equal loads, there is no current flowing through the current windings of the relays. As soon as a fault develops on one line, an unbalanced circuit circulates through the relays, causing the directional element contacts on the faulty line group to close and those of the good line group to open. The faulty line circuit breaker is tripped by the closing of the contacts of the overcurrent element having the short time setting. As soon as the faulty line circuit breaker is open, the control circuit to the short time overcurrent element is broken by the series connection through the circuit breaker auxiliary switches. The remaining line then has directional overcurrent protection only, the time and current settings of the overcurrent element being determined by operating conditions on the loop. It is general practice to base such settings on the assumption that, with a loop composed of normally balanced lines, not more than 2 sections will be operating as single lines. It is interesting to note that this scheme of connection obviates the use of a circuit opening definite time delay direct current relay to prevent improper operation of the good line circuit breaker. It has been found necessary in many instances to employ such relays with cross-connected schemes in order to prevent unnecessary tripping. Balanced power relays are satisfactory, particularly where there is no source of power available at one end of the parallel lines, but the use of differential current relays is simpler and is usually preferred where power can be supplied from both ends of the group of lines. Type CD Selective Differential Relay Scheme. Another scheme which is coming into common use for parallel line protection is a scheme using the balanced current relay known as the Type CD relay. It may be used at the transmitting end of any number of parallel lines and at the receiving end of any number of parallel lines in a system having a source of power at both ends, or at the receiving end of 3 or more parallel feeders in a radial system. It cannot be used on a single pair of radial parallel feeders, for in case of a fault on one line, there would be an equal and opposite current in the 2 elements, and the relay would not operate. The same condition will exist after one of 3 parallel lines has been disconnected at the receiving end. For this reason, cross-connected power directional relays are usually used at such points. With 3 parallel lines protected by these relays, number 1 line is balanced against number 2, number 2 line is balanced against number 3, and number 3 line is balanced against number 1. In this way, complete balance protection is secured until only one line remains in service, after which overload protection is left on this line. If 4 or more lines are thus protected, complete balance protection cannot be assured after more than 2 lines have been removed from service. Thus, with 4 parallel lines, number 1 being balanced against number 2 against number 3 against number 4, and number 4 against number 1, any one line can be disconnected and the remaining lines will still be balanced. If, however, numbers 1 and 3 lines both have been disconnected, numbers 2 and 4 will be left with only overcurrent protection. On the other hand, if number 2 or number 4 lines were disconnected, with number 1 remaining, 2 lines would still be balanced. Inasmuch as the action of the balanced current relay is practically instantaneous in clearing faulty lines, it makes an ideal application for the protection of parallel lines between generating stations. On other parallel feeders, it is often very advisable to use overcurrent relays in connection with balanced current relays, thus securing single line protection in addition to quick balance protection when both lines are in service. The chief advantages of the CD balanced current relay scheme are as follows. 1. The relay operates on current alone, no source of potential being required. 2. The differential current setting is automatically doubled when one line is opened at one end. This permits the use of a minimum differential current setting and eliminates the necessity of additional apparatus in the trip circuit in order to render it non-automatic until the 2 lines are again in service. 3. Each current transformer may be grounded, thus giving maximum protection to the apparatus. This is not possible ordinarily with balanced protection. 4. Only one relay is required for 2 lines. 5. Relay action is practically instantaneous. Type CZ impedance relay. The CZ impedance relay may be used for parallel line protection in the same way as the CO and CR relays. The CZ directional relay is applicable in places where the CR is used. The advantages of the impedance relay have been explained in detail on page 20. Network systems. The simple radial and loop or ring systems, very often involving parallel lines between stations, lend themselves very readily to a scheme of relay protection as has been outlined. However, when additional tie lines are added, connecting substations and several sources of power into the system at different points, it becomes what may be termed a network, and then the relay protection problem becomes more difficult. Type CO and CR scheme. The CO overcurrent and CR directional overcurrent relays are sometimes applied to such a system, provision being made to have certain lines trip out almost instantly with a short circuit in the vicinity. With such an arrangement, the network is often converted into a simple ring after the tie lines have been disconnected, and the usual scheme of time and current settings clears up the trouble. The cutting out of the tie line or lines in such cases does not in any way jeopardize the service, and serves to make selective relay protection possible. For example, in Figure 38, the tie line between substations E and B may be disconnected without disturbing the service supplied by the network. Type CZ impedance relay scheme. A more recent and flexible relay application for such complicated systems is the use of the impedance or distance relay. With proper application of this type of relay, all time settings are taken care of automatically, the inherent characteristics of the relay being such that the one nearest to the fault will operate first. Pilot wire scheme of relay protection. On systems where definite time relay protection is desired, the number of substations which may be connected successively in a system is limited by the sum of the time intervals which it is necessary to allow between successive relays. When such a difficulty is encountered, and the distance between some of the substations is small, a pilot wire scheme of protection may be used on the shorter sections. As this scheme acts almost instantaneously upon the occurrence of a fault within the section, and is unaffected by the faults outside of the section may be disregarded entirely when applying other relays. The system may be considered as if that particular section were entirely cut out. The pilot wire scheme has current transformers at each end of the conductor, short-circuited upon each other through the pilot wire. See Figure 40. The relays are connected between the pilot wire for each respective transformer and the common return. When a short circuit or fault occurs on the line between the two substations, the current transformers at the two ends are no longer short-circuited upon each other, but the currents which they produce are opposed to each other, so that current must flow through the relays, and the faulty section will thus be tripped out. Inasmuch as the current flowing through the pilot wire must be kept at the minimum, special current transformers and CO relays with special windings to operate on low current are used for the pilot wire protection scheme. Split conductor scheme. The split conductor scheme is a modification of the current balance scheme of parallel line protection, in which a special cable is used to obtain a division of the current which is susceptible to being balanced. As ordinarily installed, the split conductor cable is a 3-strand cable in which the strands forming each conductor are separated into two parts, a central portion and a circumferential portion, the two being separated from each other by the necessary insulation. Thus, by the use of current transformers, a differential connection between the two halves of each conductor and overcurrent relays connected in the circuit, a very effective system of protection is obtained. This system is not widely used in the United States, due largely, perhaps, to the high cost of the special cable. End of Chapter 3, Part 1. Chapter 3, Part 2 of Silent Sentinels by Westinghouse Electric and Manufacturing Company. This LibriVox recording is in the public domain. Section 3. Methods of clearing ground faults. Solidly and low-resistance grounded neutral systems. These systems, when protected by type CO, CR, and CD relays, require no additional relays for wire-to-ground faults. 3 current transformers and 3 relays are necessary for the complete protection of each circuit breaker. However, Where Type CZ impedance relays are used in order to obtain the minimum time for clearing faults, two sets of impedance elements are required for phase-to-phase and phase-to-ground faults. The reason for this is that a ground fault on one wire results in 57.7% voltage being maintained across two sides of the voltage triangle and 100% voltage across the third side. The voltage between the grounded wire and neutral is of course zero, or nearly so. If only three elements, having their directional element potential coils connected in star, are used, a wire-to-wire short circuit will reduce the voltage across each relay coil from 57.7% of the line voltage to 28.8% line voltage, so that each relay still has 50% normal voltage impressed across it. With 50% normal voltage acting on the potential coil of the CZ relay, the time required to close the contacts is entirely too long for satisfactory operation, and two sets of elements must be employed for complete protection. Medium resistance grounded neutral systems. Relay equipment, in addition to that required for line short circuits, is required to care for phase-to-ground failures. For those installations, where the magnitude of the ground current in the circuit and the ratios of the current transformers are such as to produce a single-phase current of at least 2 amperes in the secondary of one current transformer for a fault from that wire to ground, a Type CO relay having a low current winding is inserted in the neutral connection between the neutral point of the line relays and the neutral point of the current transformer secondaries. The low current Type CO relay has taps for operation at 0.5, 0.6, 0.8, 1.0, 1.5, 2.0, and 2.5 amperes. It can generally be operated on the 0.5 ampere tap without danger of tripping improperly, as under normal operation there is no current flowing in the neutral connection. Figure 41 shows the connections for the ground relay when the circuit breaker is controlled by Type CO overcurrent relays. It will be observed that the tripping contacts of the ground relay parallel the tripping contacts of the line relays. The same scheme of current and tripping connections is employed when non-directional single impedance element Type CZ impedance relays are used to protect the feeder against line faults. When the circuit breaker is controlled by Type CR directional overcurrent or Type CZ single impedance element relays for phase-to-phase faults, the low current relay is inserted in the neutral circuit for ground fault protection. The tripping contacts do not, however, go directly to the circuit breaker trip coil, but are connected in series with the directional contacts of the line relays to secure proper directional indication on ground faults as well as line faults. A tap must therefore be provided on the line relays between the directional element contacts and the overcurrent or impedance element contacts. Figure 42 shows the connections using 3 Type CR line relays and 1 Type CO low-energy ground relay. The same tripping circuit connections hold when Type CZ impedance relays are used for line faults. This arrangement should be used with care. It has been found that a high resistance at the point where an accidental ground occurs will limit the current to such a small value that the load current flowing through the CR relays will be greater than the ground current, and the CR relays will not operate in the proper direction. A low current Type CD selective differential current relay is available for ground protection at those locations protected against line faults by Type CD relays. Each winding is provided with taps for 0.5, 0.6, 1.2, and 2.0 amperes operating current. One winding is connected in each neutral connection of the balanced pair of lines. Figure 43 shows the complete connections for line and ground protection on 2 balanced lines for both balanced and single line operation. High resistance grounded neutral system. Protection against wire-to-ground faults on high-resistance grounded neutral systems cannot be readily provided unless the magnitude of the ground current in the circuit and the ratio of the current transformers are such as to provide 1.5 to 2 amperes in the secondary of one current transformer with a ground fault on that wire. Since the ground current is less than the load current in the circuit to be protected, a directional element which shall be independent of load is required. Figure 44 shows complete line and ground protection for 2 parallel lines on a high-resistance grounded neutral system. The line potential transformers are connected star-star, with the star points grounded. The line relay potential coils are energized by the delta voltages of this bank. If the potential transformers are chosen as to give 115-volt single-phase secondary when energized by a single-phase voltage of line-to-line value, the line relay should be provided with 125-volt potential coils. The secondaries of the line potential transformers also energize an auxiliary bank of 3 200 to 100-volt potential transformers connected star on the primary side, the star point being connected to the two star points of the line potential transformers. The secondaries of the auxiliary bank of transformers form a closed delta through the potential coil of the ground relay. A low current, low energy directional type CR relay, having the same current winding as the low current type CO previously mentioned, is required for ground protection. The current coil of this relay is connected between the neutral point of the current transformer secondaries and the neutral point of the line relays. When a fault from one wire to ground occurs, the distortion of the voltage triangle caused by current being fed to the ground fault by the potential transformer develops sufficient voltage across the potential coil of the directional relay to obtain, in conjunction with the residual current in the relay, the proper directional indication. The proper time of operation for the relay is secured by an adjustment of the time index lever of the overcurrent element. When power transformer banks are connected star delta and the star point is grounded through a resistor, the potential for the directional ground relays can be secured by connecting the primary of a 200 to 100-volt potential transformer between ground and a point on the resistor which is 200 volts above ground when carrying the maximum ground current. The secondary of the potential transformer energizes the potential coil of the relay. Section 4. Calculation of short circuit current. In applying any protective scheme, it is necessary to determine the short circuit currents which may develop under all conditions. It is unfortunate that the term overload has ever come into use in connection with sectionalizing distribution systems, because it implies that the relays should be set to operate at a value determined by the normal load on the feeder. Such a setting is possible if definite time limit relays are used, but where a relay having inverse time characteristics is used, it is necessary to consider the current that occurs during times of trouble, and that may be tens or even hundreds of times greater than the normal current. An approximate method of determining the possible short circuit current is to observe the voltage drop between two stations at normal load. Short circuit current equals normal voltage divided by voltage drop times load current. For example, if a certain load current causes a drop of 5% in voltage between the generating station and the substation, the maximum short circuit current would be 20 times the load current. Results obtained in this way are likely to be too large, particularly in lines having high inductance. In order to determine more accurately the RMS current, an analysis of short circuit phenomena on an alternating current network is necessary, and it may be desirable to call attention to some of the conditions under which relays may be called upon to function. A short circuit is a transient condition, and this current at any point in an electrical system is a variable depending on the resistance, inductance, electrostatic capacity, magnetic capacity, point on the voltage wave at which the disturbance takes place, and current conditions of the circuit immediately preceding any change in the steady condition of that circuit. It represents a readjustment of the stored electromagnetic and electrostatic energy in the system from an initial steady state condition until a final steady condition is reached. It is manifested during every change in the steady condition of the circuit, although its effects on the circuit are usually not appreciable. Under certain conditions, such as short circuits, the effects of the transient current, however, are of prime importance. Short-circuiting a system at any point immediately causes an abnormal current rush to occur on that system. During the first complete cycle following the short circuit, the current usually rises to maximum value. If, now, the generator field circuit is assumed to remain unchanged by automatic generator voltage regulators or similar devices, then, during succeeding cycles, the current will rise to lesser and lesser values until a steady condition again exists on the system. The current wave during the transient period, as shown by oscillograms, may be symmetrical or asymmetrical with respect to the line representing zero current, depending on the point on the voltage pressure wave at which the short circuit occurred. The transient current is said to be symmetrical when the assumed line connecting points on the current wave midway between the peaks coincides with the line of zero current. Similarly, a transient current is said to be symmetrical when the assumed line connecting points on the current wave midway between the peaks does not coincide with the line of the zero current. The value of the current at any point on the current wave during the transient condition, if referred to the line representing zero current, is a measure of the effects produced by the current at that point. Some of these effects are indicated by the breaking of insulators supporting buses, the displacing of windings of transformers and generators, the distortion of oil circuit breaker connections, and the fusing of conductors in various parts of electrical systems. The value of the current at any point on the current wave during the transient condition is frequently referred to an assumed zero line between the peaks. This value is used to calculate the electrical constants of a circuit, such as impedance, reactance, etc. The maximum asymmetrical value of a transient current in RMS amperes during a short circuit on an ordinary alternating current generator is approximately equal to 1.8 times the generated voltage, pressure, of the generator, in volts, immediately preceding the short circuit, divided by the impedance of the circuit in ohms between the point of power supply and the point of short circuit. The maximum symmetrical value of the transient current is approximately equal to 0.55 times the maximum asymmetrical value. The transient of an electrical system at a point remote from the source of power supply will be different from that at the terminals of an alternating current generator. Its amplitude and duration will depend upon the electrical constants of the system and the distance between the point of short circuit and the source of power supply. In general, the greater the distance between the source of power and the point of short circuit, the less the amplitude of the transient and the shorter its duration. Automatic generator voltage regulators introduce system transients differing from those which occur in systems not so equipped. They tend to maintain constant the system pressure, but on account of the inherent time lag of the iron portions of the generator and exciter armatures and fields, their effect is not felt immediately. The effect of automatic voltage regulators on system transients may be predicted for any known set of conditions and account taken of such effects in the application of relays. Figure 45 is a typical oscillogram showing the current flowing in one phase of the external circuit when a system is short-circuited under ordinary operating conditions. In this diagram, O is the origin of the coordinates and is taken at the instant at which the short circuit occurs. OX is the axis of the abscissa, and the abscissae represent time. OY is the axis of ordinates, and the ordinates represent current. CD is a curve passing through the maxima of the wave of total current, and EF is a current passing through the minima. AB is a curve which cuts the vertical everywhere midway between CD and EF. The wave of total current, which the crests lie along curves CD and EF, and of which ordinates are measured from the axis OX, may be regarded as having two components, namely, 1. A direct component, 2. An alternating component. The direct component is represented at any time by the ordinate to the curve AB, or at the time x by the coordinate GH. The alternating component is a wave whose crest value at any time is the difference between the ordinates to the curves CD and AB. This difference, at the time x, has the value Hj. The RMS values of this alternating component are shown on curve ST. At any instant, this component is considered to have the same RMS value as an alternating wave of constant amplitude whose crest value is represented by 1/2 the distance between curve CD and EF at that instant. The RMS value of the total current wave under short circuit, at any instant, is the square root of the sum of the squares of the value of the direct component and the effective value of the alternating component at that instant. The correct application of relays to an electrical system requires that certain characteristics of the system be known or assumed. These system characteristics are 1. Normal voltage. 2. Maximum current carried by the circuit in which the relay is connected. 3. Normal frequency. 4. Maximum kVA capacity of synchronous apparatus, transformers, reactors, and lines. 5. transient current characteristics during short circuit or overload. The RMS current at any point of a system under short circuit conditions is affected by the following factors. 1. The total kVA, reactance, and transient characteristics of the synchronous machines connected to the system. 2. Number, reactance, resistance, capacitance, and arrangement of all circuits over which power can be supplied to the point of short circuit. 3. kVA, arrangement, resistance, reactance, and capacitance of all reactors and transformers through which power can be supplied to the point of short circuit. 4. Contact resistance at the short circuit. 5. The nature of the short circuit, whether single-phase or polyphase. 6. The kVA and power factor of the load being carried at the time of short circuit. 7. The point of the voltage, pressure, wave at which the short circuit was established. 8. The use of automatic voltage regulators. The short circuit transient for systems may be determined by test, by calculation, or, less closely, by assumption. Obviously, the determination by test for all circuits of a large system is expensive and involves considerable time and interruption to service. This will be practical in but a few cases. The determination by calculation is also a matter of considerable labor, but is feasible if only the important factors listed above are considered. Practical approximate selection, sufficiently accurate for most cases, can be made by using only reactance and an accepted group of time current decrement curves. Table 1 gives decrement factors for three-phase short circuits. These factors are intended primarily for use in relay application and setting, where minimum short circuit values are important. The effect of using RMS values instead of peak values is to appreciably reduce the ratio between short circuit and rated amperes. For example, assuming 10% reactance and a short circuit current containing the maximum possible direct component, the ratio of the peak value of the first alternation of the short circuit current to the peak value of rated current is roughly 20. Under the same conditions, the ratio of the RMS value of the first alternation of the short circuit current to the RMS value of the sinusoidal rated current is roughly 17. The effect of using the flux at rated voltage and the assumed load instead of at rated voltage and no load is to increase the short circuit current by a somewhat lower percentage than the alternator reactance percentage. This effect in alternating current generators of low reactance is relatively unimportant, but becomes of increasing importance as the generator reactance increases. The characteristic shapes of the time current decrement curves have been reached by analysis of generator tests, including oscillograph studies of short circuits occurring when the generators were excited to full voltage and were carrying various loads at various power factors. In the curves for total reactances, up to including 15%, the reactance is assumed to be wholly within the alternating current generators. And for higher values of reactance, the generators were taken at 15% and due allowance was made by calculation for the effect of the external reactances. In the latter case, if alternating current generators of the other reactants had been used, the results would have been somewhat different, but the error is not large enough to be of practical importance. The final values of current, i.e., the sustained short circuit current, have been assumed in accordance with experience and tests and are based on the behavior of machines of predominating design. The study of representative oscillograms of short circuit tests showed that in most cases, the direct component disappeared within 0.5 seconds, and that the transient portion of the alternating component disappeared within 3 seconds. These time values have therefore been used in constructing the characteristic decrement curves. Several alternating current generators with the same reactance and synchronous impedance will not necessarily have the same rate of RMS current decay. This has been considered in constructing the characteristic curves, and the decrement curves may therefore safely be taken as representing the greatest RMS current that will be given by modern alternating current generators of normal design. The percentage reactance in any leg of a circuit is the reactance drop in that leg of the circuit at normal rated current expressed as a percent of the voltage to neutral of that circuit. For single and two-phase systems, This is the voltage between phased wires divided by 2. For three-phase systems, this is the voltage between phased wires divided by 1.73. The percentage values in Table 1 are initial values based on a symmetrical sine wave and on the maximum rating of the machines connected to the bus. The percentage of reactance of generators varies from about 8% to 30%. The percentage reactance of transformers varies from about 3% to 15%. Nature of short circuits. When making current calculations, it should always be assumed that a short circuit is due to a metallic connection between the conductors. In a high-voltage aerial line using wooden pins and crossarms, it sometimes happens that an insulator is broken, with the result that the wood is gradually heated by the passage of the current through it until it finally bursts into flame, thus causing an arc between conductors. A little consideration shows that the flow of current is small until the arc is established, and that it is wrong to speak of automatically disconnecting a section of line which has such a high resistance short circuit. It has sometimes been assumed that an arc has a high resistance, but this is not the case, and in general the presence of an arc at the point of short circuit will not decrease the short circuit current by more than a few percent. Incidentally, it may be of interest to note that on a high voltage ungrounded neutral system, the capacity current to ground through an arc is greater than it is through a direct ground. There is only one case where a short circuit is likely to increase in intensity as it develops, and that is on a system where the neutral is grounded through a resistance. A cable breakdown, for instance, frequently occurs first between one conductor and the sheath, and the current flow may be limited by the neutral resistance. The trouble will quickly involve all the conductors in the cable, resulting in a heavy short circuit, but it is possible that it will require an appreciable time to do this, in which case the relay operation may be unsatisfactory. This is particularly liable to happen if the neutral is not grounded at every substation. Section 5. The protection of AC apparatus. Overload protection. Overload protection of the larger type of electrical apparatus, as a general rule, receives little special attention, inasmuch as the relays provided for short-circuit protection serve also for overload protection of the apparatus of the system. In addition to this, in generating and substations where there are operators in attendance, the load on the apparatus is usually under their supervision and is governed by them accordingly, except in cases of short-circuit trouble on the system. In small installations where some scheme of overcurrent protection is necessary, the CO overcurrent relay, or CW over power relay, can generally be used to give satisfactory protection. Protection against internal faults. Protection against internal faults in the windings of electrical apparatus is receiving much attention in present-day practice. These internal faults might be roughly classified as phase-to-phase short circuits, short-circuited turns, open circuits, and grounds. Experience has shown that most of the internal faults developed in larger types of rotating electrical apparatus develop originally as a ground from the phase windings to the frame. If the neutral is not grounded, a fault of this sort will not unbalance the phase current, and it is, therefore, rather difficult to locate until it is developed into a phase-to-phase short circuit. Thus, from the consideration of protection, it is best, wherever possible, to have the neutral grounded. Grounds are more likely to occur near the line end rather than the neutral end of a winding, but in the event of the latter, the current which flows may be relatively small, especially if a high-resistance ground is used. The fact that the fault current is often very small at the beginning, and that it is highly desirable to detect such a fault and disconnect the apparatus from the line before a phase-to-phase short circuit can develop, makes the protection of apparatus against internal faults rather a difficult problem. A differential scheme of protection, making use of either standard overcurrent relays or special overcurrent relays operating on very small current, is the most general scheme for protection against internal faults. This form of protection consists of balancing the current entering the apparatus against the current flowing from it. This scheme of protection is usually accomplished by connecting a current transformer at each end of each phase winding, connecting their secondaries in series, and then connecting a current relay across these secondaries. As long as the secondary currents are equal, no current will flow through the relay windings. Any leakage of current, however, to other phases or to ground, will upset this balance and send current through the relay. The relay in turn operates to trip the circuit breaker and disconnect the faulty apparatus. The principle of operation used in this scheme allows relatively low current settings on the overcurrent relays, because obviously no current will flow under normal conditions. It is also free from trouble due to circulating current, when synchronizing or switching on any part of the system is taking place, inasmuch as such current should be balanced in each phase. This scheme is very flexible in its application and might be applied to machines of any size, either star or delta connection, provided that both ends of each phase winding are capable of being brought out and connected to current transformers. No definite rule can be set down in regard to the size of apparatus to which relay protective scheme should be applied. It is largely a question to be decided from a consideration of the importance of limiting the amount of damage that can be done to the machine. In other words, it resolves into an economic consideration in which the cost of relay protection must be balanced against the value of service rendered, and then compared with the cost of possible damage to the apparatus. In the case of large generators and sometimes motors, where the neutral is grounded directly or through resistance, and the faulty currents may or may not be of any great value, a relay sensitive to very small current is required. The low-energy CO relay is especially adapted for the differential protection of such applications. An improvement on this method has been made by designing a relay, the type CA, that trips on a percentage of the line current rather than on a given value of current. This makes it possible to get more sensitive protection without danger of having the relay operate due to the circulating currents, which usually occur at times of through short circuits. In the differential protection of transformers, highly sensitive settings are not so necessary, and in many cases are undesirable, as they would only serve to disconnect the transformers upon some transient condition which accompanies a momentary unbalance, but not a fault. The standard overcurrent CO relay is, therefore, applicable for the differential protection of transformers. A special form of the Type CA relay, with taps provided so that unequal currents can be balanced without the use of autotransformers, has been developed for transformer protection. This tap arrangement, combined with its adaptability to cases where circulating current appears under transient conditions, makes it of particular value, especially when bushing-type transformers are to be used. Open or reverse phase protection. In many installations of polyphase motors and rotary converters of any size, it is becoming a common practice to provide protection against running in case of an open phase or in case of reversal of phases. A reversal of two phases, of course, reverses the direction of rotation of any motors on the line, and so it is especially desirable to have this condition protected against in cases where a reversal of the direction of rotation of any driving motor, such as one in an elevator service, may be disastrous. The CQ phase balance current relay gives ample protection against the occurrence of such conditions on a system. Temperature protection of windings. Inasmuch as the overheating of the windings in electrical apparatus is closely related to the overcurrent protection, the overcurrent protection is often adequate to provide the necessary temperature protection. In some cases, however, it is more desirable to furnish protective apparatus which will include, in its operation, not only the load on the apparatus, but also the existing temperature of the windings. In other cases, the temperature of the winding alone is taken as the determining factor in the operation of a temperature protective scheme. In most of the larger generating stations or substations, where constant supervision of the operation of the various machines is possible, temperature indicating devices are used to show the attendant when the temperature of the windings in question becomes such that some means should be used to reduce it. Such indications are usually provided by means of exploring coils, embedded in the windings of the apparatus, serving either to actuate a signal when the temperature reaches some predetermined point, or to operate some temperature indicating instrument. Thus, when the critical degree of heat is indicated, the operator may relieve the condition either by reducing the load on the apparatus or by increasing any existing cooling means, such as the flow of air or water, as the case may be. Oil-filled thermal relays. Where manual supervision is not possible, such as in automatic substation equipment and in plants using numerous motors, it is necessary to have temperature protection that will disconnect the apparatus when any predetermined conditions exist. A common scheme for providing such protection is to apply in a protective relay a heating element with thermal characteristics similar to those of the machine to be protected. A current proportional to the load current in the apparatus itself flows through the heating element of the relay. The characteristics of this element are such that its temperature will be approximately the same as that of the protected apparatus under all loads and at all times. When the temperature of this element reaches the critical point, it serves to trip the apparatus offline. The Westinghouse BA and BD oil-filled thermal relays serve to provide this class of protection. Type CT temperature relay. Another scheme used for the temperature protection of windings is to have the protective apparatus dependent on the current flowing at any given time, and also at the same time on the temperature within the windings of the apparatus to be protected. In such a scheme, the temperature is usually determined by means of copper exploring coils buried in the windings, and connected in some sort of bridge arrangement, so that the change in resistance of the exploring coils, due to any change in the temperature of the windings, will give the proper temperature indication to the protective relay by using the change in the resistance values to cause a flow of current. In addition to this, a current proportional to the current flowing in the apparatus flows through another winding of the relay, and thus the following three conditions are necessary before the apparatus is disconnected from the source of power. First, the temperature of the windings of the apparatus must be above the value for which the relay is set to operate. Second, the current flowing in the apparatus must be above the normal value. And third, these two conditions must have existed for a given period of time. Thus, the liability of the machines being disconnected upon the occurrence of a transient overload is guarded against. The CT temperature relay provides such protection and embodies the necessary characteristics to assure maximum continuity of service. The simplest form of over-temperature protection is that in which the temperature of the surrounding material is alone used as an indication of the temperature of the winding, and is taken as the determining factor in the operation of any protective relays used. Such a scheme is used largely in the protection of transformers where the exploring coils, expansion bulbs, or whatever means are used for measuring the temperature of the surrounding material may be embedded between the coils of the transformers in such a way that an approximate indication of the temperature of the windings is secured. The HM thermostat relay is sometimes used for this purpose. Temperature protection of bearings. In the case of rotating machinery, it is often necessary to provide some scheme of protection whereby any overheating in the bearings will either cause a signal to operate or else cause the machine to be disconnected entirely. Where actual supervision is possible, such protection may provide only for the operation of a signal to call the attendant's attention to the fact that all is not well with his machinery. In cases such as automatic substations, it is usually necessary to have the protective apparatus disconnect the machine entirely, either shutting down the station or else disconnecting the individual piece of apparatus. The HM thermostat relay is used largely for this application. End of Chapter 3, Part 2. Chapter 4 of Silent Sentinels by Westinghouse Electric and Manufacturing Company. This LibriVox recording is in the public domain. Direct current systems. The direct current systems of today, though small in comparison with the alternating current systems, offer relay problems equally important. Comparable to the service demanded of other public utilities is that which congested cities demand from street railway companies. The growth and interconnection of some of these systems have created a demand for adequate direct current relay protection. This demand for service brought about both the development of service restoring equipment and the supervision of feeder apparatus by supervisory control. Protection against overcurrents, caused either by accidental faults on feeders or lines, or by excessive overloads on lines, can be affected by the use of overcurrent relays. The short-circuit detector type of equipment, meeting the demands of railway systems, permits heavy overloads due to acceleration, but gives protection upon the occurrence of a short circuit on the line. Service restoring system. As in the case of alternating current service, the question of continuity of service often makes necessary some sort of device to restore service after it has been interrupted. Where a feeder has been tripped out because of a fault, It may sometimes be necessary to provide means for automatically reclosing the breaker several times, allowing a definite interval of time between each reclosing. Thus, if the fault is of a transient nature and clears itself quickly, the breaker will remain closed, and service will be continued on the line. However, if the fault is of a permanent nature, the breaker will open each time it is reclosed until the specified number of reclosures have occurred, and then it will remain open permanently, indicating that the line requires attention. Another method used for service restoring is to have a relay which has included in its design characteristics whereby it discriminates between a good and a bad feeder. In this case, the feeder is opened under overcurrent or short-circuit conditions, and the breaker is reclosed automatically as soon as the excessive load is removed. After the breaker has been opened, it may be reclosed by a resistance measuring relay. This relay determines when the fault has been cleared sufficiently to allow the circuit breaker to be closed with safety. When continuity of service is of great importance, and when the capacity behind the feeder is large, it is desirable to have the breaker remain closed, except in cases of actual short circuits or violent overloads. Operators of large urban railway systems demand this class of service, as it permits heavy peaks for acceleration of the cars and prevents untimely interruption of the service. Nevertheless, in meeting this demand, the feeder circuits must be protected against short circuits and heavy overcurrents. The short circuit detector type of equipment provides this protection without interrupting the circuit on ordinary overloads. Except for heavy railway service, it is usually desirable to open a circuit on a definite overcurrent. For this application, the overcurrent type of equipment with an overcurrent relay is used instead of the short circuit detector. The overcurrent setting is usually for instantaneous tripping, but occasionally a time element is provided. Protection of direct current apparatus. The protection of the direct current apparatus might be classified as protection against overcurrent, reversed current, and overtemperature. In most cases, such protection on motors and generators is secured by means of circuit breakers equipped with necessary overcurrent or reversed current coils, or by fuses of suitable capacity. In many installations, however, it is found necessary to use a protective relay in order to secure the needed accuracy and reliability of protection. In such cases, the D or TO overcurrent relay is used, and in cases where protection is required against reverse current, the D reverse current relay is applicable. Overtemperature protection of direct current apparatus is obtained in a manner similar to that described under alternating current apparatus. The BD oil-filled thermal relay is used largely for motor protection, while in some cases where it is possible to have exploring coils in the windings, the DT temperature relay is used. Electrochemical work. When a line supplies a load for such work as electrochemical processes, where a reversal of polarity is extremely dangerous, it is sometimes necessary to supply a highly sensitive relay which serves to disconnect the circuit when any condition shows that the polarity is liable to reverse. The apolarity directional relay has been used very successfully for this purpose, fulfilling the protective requirements and passing the underwriter's inspection. The sensitivity and design of this relay are such that the contacts will be closed upon any reversal of the polarity of the circuit to which it is connected, or upon a fall in the voltage to below 20% of normal value. End of Chapter 4.
Chapter 5 of Silent Sentinels by Westinghouse Electric and Manufacturing Company. This LibriVox recording is in the public domain. Automatic control. Substations, depending on the method used in their operation, may be divided into 3 classes: manual, semi-automatic, and automatic. Regardless of its type, a station must be a highly reliable source of power supply. The necessary operations in a substation, which serves the purpose of transforming alternating current into direct current by means of synchronous converters or motor generators, are, therefore, the starting and stopping of such machines when the system demands it, and the provision of adequate protection against faulty action either in case of some trouble out on the system or in case of trouble within the substation equipment. The automatic substation today is more dependable than is the manually operated station. The design and development of relays with a high degree of accuracy, sensitivity, and reliability have made such an automatic substation a possibility. The characteristics of the automatic substation, which must be supplied by adequate relays, might be roughly divided into two classes, namely control and protection. The control methods consist in the automatic starting of one or more of the machines in the station. This may be introduced in any one of several ways, depending on the conditions to be met, and is generally accomplished through some form of remote control or by means of a voltage relay which closes its contacts at some predetermined value of reduced line voltage. Starting due to momentary drop in voltage or when the alternating current voltage conditions are incorrect is prevented by an induction type alternating current voltage relay. While many of the operations are common to both synchronous converters and motor generators, the following outline of system is especially applicable to synchronous converters. When conditions are favorable for starting, a sequence of relay actions serves to perform the necessary functions, such as lifting the converter brushes, connecting the converter to the starting tap of the power transformers, and other operations depending on the type of substation. After the converter has started to rotate, synchronism and polarity are indicated by a polarized motor relay, which in case of reversed polarity causes the polarity of the machine to be corrected by reversing the field. The armature of the relay motor is connected to the converter pilot brushes, and during the period of starting, the polarity of the relay becomes that of the machine. As the converter comes up to synchronous speed, alternating current of diminishing frequency flows through the motor armature until synchronism is reached without causing rotation. At that time, the armature will revolve and drive a drum switch in the direction corresponding to the converter polarity. If the polarity is incorrect, the drum switch causes the field connection to reverse by means of a double-throw contactor switch. The reversed connection is maintained only long enough for the voltage to fall to zero and then to release the controlling relay, which causes the normal field connection to be re-established. By this operation, the converter has been caused to slip a pole and thus correct the polarity. The polarized motor relay continues to operate and causes a transfer relay to function. This relay, in turn, opens the starting contactor, causing operation of the direct current brush operating mechanism, which lowers the brushes to the commutator. At this time, the main direct current switches are closed and the machine is connected to the load. The final function of the control part of the substation equipment is to disconnect the machine from service. This operation is introduced by the action of a sequence of light load control relays. Protective equipment is provided not only in the automatic substations, but also in the manually operated or the semi-automatic stations. It is provided by induction-type single and polyphase relays, which prevent the station from starting under abnormal conditions of alternating current line voltage, such as low voltage, open phase, or reverse phase. The same type of relay causes the station to shut down on unbalanced phase conditions. If the trouble is within the station, a lockout relay prevents restarting, and if the unbalanced phase condition is outside the station, the automatic equipment functions to bring the apparatus into service as soon as the line is restored to normal. Each bearing is equipped with a thermostat which, in case of a hot bearing, locks the machine out of service until the contacts of the thermostat device have been reset by hand. A thermal relay also protects the winding of the machine from overheating due to continued overload. Other protective devices are the direct current directional relay, an overspeed device, an inductive type alternating current overload relay, a thermostat preventing overheating of the current limiting resistors, and a lockout relay which locks the equipment out of service in case of failure of any part of the apparatus. The protection of the equipment is complete and responds immediately in case of trouble, thus eliminating the losses which often occur in manually operated substations because of the very impossibility of handling an emergency in the required time or the inability of the operator to do so. In addition to this automatic operation of the substation, a number of automatic selective relay equipments are in use for automatically cutting out a short-circuited line or for automatically reclosing and other types of necessary feeder operation. It can be seen from this description what a large part the relays play in automatic substation equipment, and also how absolutely necessary it is to have relays which are not only highly reliable and accurate at the time of their installation, but also which will maintain this high degree of accuracy and reliability throughout continued service. The success of the Westinghouse automatic substations and past experience have proved the induction types of relays, first developed and manufactured by the Westinghouse Company, to be especially suitable for this type of service. By the use of the induction type relays, precision of operation is not only assured, but the exact calibration can be maintained throughout a long period of operation. Thus, the induction relay has solved many of the difficulties which were formerly experienced when plunger-type relays had to be depended on for various functions. Most of the relays supplied with the present-day automatic substation equipment are standard protective relays, as described elsewhere in this publication. In some cases, it is necessary to somewhat modify the characteristics of the relay, but the fundamental principles of design and operation are maintained. The CV voltage relay is used throughout as a timing voltage relay to provide a definite time delay where necessary. A slight modification of this relay consists in having the contacts geared to the disc shaft rather than mounted directly on it, which provides a relay with a much longer time delay characteristic than the standard. The GK time delay relay, also used largely in automatic substation equipment, is motor operated and is highly reliable. A recent addition to the relay family is the MF flash relay, which is used in automatic substation protection to disconnect the rotary in case of a flashover occurring between the commutator and the frame. End of Chapter 5. Chapter 6 of Silent Sentinels by Westinghouse Electric and Manufacturing Company. This LibriVox recording is in the public domain. Relay Settings. The selection of the proper current tap and time index lever setting for induction-type overcurrent relays demands a knowledge of the load conditions in the circuit or portion of the circuit to be protected, and the amount of short-circuit current available under minimum generating capacity conditions. It is also desirable to know the amount of short-circuit current available under maximum generating conditions, but in case the data is not available, the interrupting ability of the oil circuit breaker will serve as a first approximation. While there are minor modifications in the actual settings of the relays dependent on the particular type of protection employed, the following remarks will outline the general considerations with reference to the simpler cases. Current tap settings on radial and loop feeders. The proper current tap is determined largely by the current transformer ratio and the full load current in the feeder. In general, the current tap is so chosen to be at least 200% of the secondary current from the current transformers when carrying full load in the line. In cases where the load is subject to violent fluctuations, it may be necessary to make normal operating current for the relay 300% of the secondary current corresponding to normal full load. The current tap should not, however, be chosen so high that the relay winding receives less than 300% of its current setting under short circuit with minimum generating capacity on the system, as otherwise the time of operation will be so long as to completely disrupt service. Time settings on radial feeders. The proper time of operation of the relay is determined by its location with respect to the source of power and other relays on the same circuit. For a radial feeder system, the outermost relay is set for the shortest time, and the relays toward the generating station for successively longer times. The relays at the source of power must be set sufficiently long to allow any outlying faulty section to be cleared. With induction-type relays and direct current-operated circuit breakers, it is common practice to set successive relays for time intervals 0.5 seconds apart with the outermost relay set for 0.1 second. Adopting a maximum of 2.1 seconds as the longest time a fault should remain on the system, we therefore find that 5 sections is about the most that should be protected by selective timing alone. Although some systems are operating satisfactorily with relays set 0.3 or 0.4 seconds apart, such systems achieve success only by extreme care in the maintenance of the oil circuit breaker mechanism and careful adjustment of relays and trip circuit mechanisms. Time intervals closer together than 0.5 seconds are not to be recommended for average systems. The time of operation should be that required when the relay is operating on the flat or minimum time interval of the time current curve, i.e. when the second current is 500% or more of the relay current tap setting. Time settings on loop feeders. For the simple loop system involving only one source of power, the relay time settings are described in the paragraph on time settings on radial feeders. The loop is opened at one of the generating station breakers, and the relays on the outgoing sides of the substations set for successively higher times of operation from the outermost substation, considering the feeder as straight radial to the generating station. The loop is then closed up and the other generating station breaker opened, the time settings on the remaining relays being determined as already outlined. Starting on the loop at any point and approaching the generating station, it will then be observed that the relays set to trip for power flowing from the generating station will be set for increasingly longer times of operation, whereas the relays set to trip for power flowing towards the generating station will be set for increasingly shorter times of operation. The loop system, which receives power at 2 or more points in the ring, is especially difficult to relay. If the various substation relays are timed for one source of power, as outlined in the preceding paragraph, the timing is wrong when considering the other source or sources of power. Parallel lines between any 2 points can, of course, use some form of balanced protection for parallel operation, but this is not applicable when the lines are operating singly. In applying a series of time settings to such a system, it is generally necessary to consider both the amount and source of short-circuit current available. Selection usually can be obtained by working on the inverse portion of the time current curve of the relay. Parallel feeders protected by type CD relays. For lines protected by type CD relays, it is usual to set the relay to operate on a differential current of 3 amperes. For through short circuits, the current in the two equal lines will be balanced so that there will be a very slight amount of differential current tending to trip the relays. For the somewhat infrequent case where type CD relays protect two parallel lines of unequal impedance, but equipped with current transformers of the same ratio, type A current balance autotransformers should be used to make equal the currents flowing through the relay windings. The time setting is generally on the order of 0.1 or 0.2 second. Settings for ground relays. Ground relays are set the same as line relays, except that ground current flow differs in magnitude from the current flow for a line-to-line short circuit. End of Chapter 6. Chapter 7 of Silent Sentinels by Westinghouse Electric and Manufacturing Company. This LibriVox recording is in the public domain. Typical relay application. When it is desired to relay a power transmission system, there are many factors which enter into the problem, all of which must be given consideration. In most systems, so many complications are present that it is almost impossible to secure an ideal application of relay protection. However, in most cases, it is possible to arrange the relay settings so that certain lines, in case of a fault, may be disconnected without disturbing the service, and the disconnecting of these lines leaves conditions such that ideal selective action is secured on the rest of the system. Where distance between stations is great enough to give the necessary 3% drop, and it is convenient to use the type CZ relay, these complications may be eliminated. Figure 64 shows a schematic sketch of a typical network system, which will be used as the basis for illustrating one method of making an initial relay application. Figure 64 is described here in order to facilitate understanding the remainder of the chapter. It is suggested to copy this down to paper to facilitate understanding. The Crichton generating station is connected via a loop system to 7 substations. Line 1 connects Relay 22 at Crichton Generating Station with Relay 1 at Woodward Sub. Line 2 connects Relay 21 at Crichton Generating Station with Relay 2 at Woodward Sub. The distance is 3 miles. Fault location A is located on line 1. Line 3 connects Relay 3 at Woodward Sub to Relay 4 at Parsons Sub, over a distance of 3 miles. Fault location B is on this line. Line 4 connects Relay 6 at Parsons Sub with Relay 7 at Breisky Sub. Fault location C is on this line. The distance is 6 miles. Line 5 connects Relay 8 at Breisky Sub with relay 9 at Feldman sub. Fault location D is on this line. Line 6 connects relay 10 at Feldman sub with relay 11 at Goldsboro sub. Fault location E is on this line. The distance is 1 mile. Line 7 connects relay 12 at Goldsboro sub with relay 13 at Kubiak sub. Fault location F is on this line. The distance is 3 miles. Tie line 8 connects relay 5 at Parsons sub with relay 14 at Kubiak sub. Fault location G is on this line. The distance is 5 miles. Tie line 9 connects relay 15 at Kubiak sub with relay 20 at Crichton Generating Station. Fault location H is on this line. The distance is 5 miles. Line 10 connects relay 16 at Kubiak sub with relay 17 at Anderson sub. Fault location I is on this line. The distance is 4 miles. Line 11 connects relay 18 at Anderson sub with relay 19 at Crichton Generating Station. Fault location J is on this line. The distance is 2 miles. End of Figure 64 description. Upon analysis, the network is found to be really a loop system with tie line number 8 connecting Parsons and Kubiak substations and number 9 connecting the generating station with the Kubiak sub. This loop, without these ties, connects 7 substations with the generating station. Either the COCR or the CZ relay scheme will be the typical one to use. Therefore, the COCR scheme will be chosen, with the CZ scheme as an alternative. Standard CO overcurrent relays are therefore allotted to each outgoing line, numbers 1, 2, 9, 11, at the generating station, and standard CR directional overcurrent relays on each line of the loop at each substation. The type CR relays are connected so that the directional element contacts will close only when power is flowing away from the substation bus bars. It should be remembered throughout this discussion that excess current flowing in this direction is necessary to complete the tripping circuit. After assigning relays to the various lines, the next problem is to assign time settings to the relays and then check out to determine if the proper time intervals necessary for selective action can be allowed without having excessive time settings on any of the relays. A 5/10 second interval between relay settings is commonly used in present-day practice, this value allowing 0.35 second for the breaker to open after the trip circuit has been made, and 0.15 second margin. The maximum allowable setting, of course, depends on the system, but 3.1 seconds is considered the highest time setting which it is safe to use, and a maximum of 2.6 seconds is adhered to whenever possible. Referring to the system in question, there are 7 substations in the loop which would require a maximum time setting of 3.6 seconds for the relays at the generating station. This value is rather high, therefore some way must be found to lower it. When checking the distance between stations, it is found that line 6 is comparatively short. Hence, a pilot wire scheme may be used to protect this section. That makes one less section to be counted in adding the successive time intervals, but 3.1 seconds is still higher than is desirable. Trying to find some means of eliminating one more section, it is observed that the Anderson sub might be eliminated from the loop for the first trial application, making tie line number 9 a part of the loop. This will make it possible to obtain the proper intervals between successive relays with a maximum setting of approximately 2.6 seconds. Definite time settings may now be assigned to the successive relays in the following manner. Beginning at the Woodward sub, the CR relays numbers 1 and 2 on lines 1 and 2 set to trip with power flowing from the sub to the generating station may be set to trip almost instantly because a fault on line number 1 or 2 is the only circumstance to cause excess current to flow in this direction, and therefore the relays may be set to clear as soon as possible. It is customary to make this setting 0.1 second. Going on to the next sub, Parsons, we find that relay 4 on line number 3 at this sub is set to trip with power flow in the same direction, namely away from the bus bars towards Woodward sub. This relay must accordingly be given a higher time setting because a fault on line 1 or 2 will draw current through relay 4, and therefore it is essential to have relay 1 trip first. A definite setting of 0.6 second is therefore assigned to it. In like manner, each successive relay connected to trip with the power flow in this direction is given a setting of 0.5 second higher than the next preceding one, which leads to a setting of 2.6 seconds on relay 20 at the generating station. Relay number 11 at Goldsboro sub may be ignored because it can be set to trip almost instantly when a fault occurs in line 6, but a fault on any other part of the system will not affect it. A similar procedure is followed out for the relays set to trip with the power flow in the other direction or clockwise, as it might be considered. Beginning at Kubiak sub, relay 15 is assigned 0.1 second setting, relay 12 0.6 second, relay 8 1.1 second, and so on, until relays 21 and 22 at the generating station are reached. The next problem which must be met and solved is the time setting for relays 5 and 14 on line 8 and relays 16, 17, 18, 19 on lines 10 and 11. No definite rule can be followed for making the settings on relays 5 and 14. Very often, the relays on a tie line are set to trip in a short time whenever excess current flows, because this action makes the relay operation on the rest of the system simpler and does not injure the service. In this case, however, by assigning a setting of 1.6 seconds to relay 5 and 2.1 seconds on relay 14, comparatively good protection is secured for line 8, and neither relay will trip with a fault elsewhere on the system except in 1 or 2 cases, as will be shown later. The lines 10 and 11 may be considered as completing the loop from substation Kubiak rather than line 9, and the settings assigned to fit in with the rest of the loop as already described. A check can now be made, assuming a fault in each line in turn, and then determining whether the proper relay operation will take place. Assuming a fault on line 1 at A, current will flow to the fault from the generator station and from Woodward sub. Thus, relay 1 will clear within 0.1 second, cutting off all flow from that direction, and relay 22 will clear within 2.6 seconds. Assuming a fault at B on line 3, current will flow in from both directions, tending to trip relays 7 at Breisky, 14 at Kubiak, and 21 and 22, in addition to 3 and 4 at the immediate ends of the line. Relay 3 will beat 22 and 21 out, thus clearing the fault in that direction, and relay 4 will trip in 0.6 second, which is a shorter period than that of any of the others that will be likely to trip. Assuming faults at C on line 4, D on 5, G on 8, E on line 6, H on line 9, J on line 11, and I on line 10, the action may be checked out in the same way. Assuming a fault on line 7 at F, we find that current may be drawn from both directions, that coming from sub-Kubiak being possibly drawn from lines 8, 9, and 10, in case enough current is drawn from line 8 to give relay 5 its definite minimum time of tripping, it may trip before relay 13 clears. However, relay 13 will trip before any other relays in the system. Therefore, the opening of the tie line is not serious. There is also a possibility of setting the current taps on relay 5 so that it will be operating on the inverse part of the curve under such a condition and thus increase its time of tripping to the extent that relay 13 will trip first. If it is desired, and an analysis of short-circuit current values shows that sufficient unbalance will exist between lines 1 and 2 with a fault in either one, additional current balance CD relays may be installed at each end. These will provide a means for clearing either line almost instantly when they are both in service and one develops a fault. Type CO relays should be used on each outgoing feeder from the several substations. Type CA relays should be used for the differential protection of the 3 banks of transformers in the generating station. The transformers in the substations also may be supplied with differential protection if their size and location justify it. In most cases, however, where the transformers are relatively small, less than 2,000 kilovolt amperes, and where the overload relays may be given a low time setting, the overload relays serve also as sufficient transformer fault protection. On complicated systems employing CO and CR relays for protection, the time required to trip sometimes becomes excessive in some parts of the system. This objectionable feature is entirely absent in a CZ installation, as all lines have their relays set to clear the line in a maximum time of 0.75 seconds, with a short at the far end. If the short takes place at or near the relay, the short is cleared almost instantaneously, since the voltage restraining action is 0. The other relays on the system are restrained in proportion to their distance from the short and accordingly do not open their breakers. Type CA relays should be used for the differential protection of the 3 generators. It should be understood that definite current and time settings and final checks on the relay operation can be made only after a short-circuit study of the system has been made, thus determining the actual currents which will flow in different lines with faults at the different locations. After this information is available, the proper current transformer ratios and current taps on the relays may be specified, and with the time setting assumed, the exact time of operation may be found from the relay time current curve. End of Chapter 7. Chapter 8 of Silent Sentinels by Westinghouse Electric and Manufacturing Company. This LibriVox recording is in the public domain. Application chart for Westinghouse protective and control relays. General applications. Application: to give signal at, over, or under AC voltage. Type CV. Rating: contacts normally closed above 55 volts, 90 volts, 140 volts, or 280 volts. Contacts normally closed below 80 volts or 160 volts. Time characteristics: inverse, operating principle, induction. Description: AC over and under voltage. Application: to disconnect AC apparatus upon overcurrent. Type CO. Rating 4 to 12 amps, 4 to 16 amps. Time characteristics: inverse with definite minimum. Operating principle: induction. Description: AC overcurrent. Voltamps required to operate: 16. Application: to disconnect AC apparatus upon overcurrent. Type COA. Rating 4 to 12 amps. Time characteristics: inverse with definite minimum. Operating principle: induction. Description: type CO with current indicator. Volt amps required to operate: 16. Application: to disconnect AC apparatus upon overcurrent. Applicable where only low ratio bushing type current transformers are available. Type LECO. Rating 4 to 12 amps. Time characteristics: inverse with definite minimum. Operating principle: induction. Description: AC overcurrent. Volt amps required to operate: 2. Application: to protect AC installation against excessive power flow in reverse direction. Normal voltage. Applicable on regenerative systems. Type CW. Rating 5 amp, 1725 volts, 50 to 300 watts, 100 to 600 watts. Time characteristics: inverse. Operating principle: induction. Description: AC reverse power. Application: to protect windings of AC apparatus from overheating. Applicable where exploring coils may be installed in windings. Operates only on excess current and temperature. Type CT. Rating 5 amps. Time characteristics: inverse. Operating principle: induction. Description: AC over temperature. Application: to protect windings of apparatus from overheating. Oil-filled thermal relay operating from current transformer. Short time. Type BA. Rating 2 to 15 amps. Time characteristics: 10 seconds to 90 minutes. Operating principle: differential expansion. Description: AC thermal. Voltamps required to operate: 16 to 52 volt amps at 5 amps. Application: to protect windings of apparatus from overheating. Oil-filled thermal relay operating from current transformer. Long time. Type BA. Rating 2 to 15 amps. Time characteristics: 10 seconds to 120 minutes. Operating principle: differential expansion. Description: AC thermal. Volt amps required to operate: 16 to 52 volt amps at 5 amps. Application: to protect windings of apparatus from overheating. Oil-filled thermal relay operating from current transformer. Long time. Type BF. Rating 1 to 60 amps. Time characteristics: inverse. Operating principle: differential expansion. Description: AC or DC thermal. Application: to protect windings of apparatus from overheating. Cartridge type thermal relay. Type BK. Rating 60 to 100 amps. Time characteristics: inverse. Operating principle: differential expansion. Description: AC or DC thermal. Application to protect windings of apparatus from overheating. Cartridge type thermal relay. Hand reset. Type BH. Rating 1 to 100 amps. Time characteristics inverse. Operating principle differential expansion. Description AC or DC thermal. Application to protect windings of DC apparatus from overheating. Applicable where exploring coils may be provided. Type DT. Rating special. Time characteristics inverse. Operating principle moving coil. Description DC over temperature. Application oil-filled thermal relay operating from bus current shunt or interpole drop. Short time. Type BD. Rating 2 to 15 amps. Time characteristics 10 seconds to 90 minutes. Operating principle differential expansion. Description DC over temperature. Application oil-filled thermal relay operating from bus current shunt or interpole drop. Long time. Type BD. Rating 2 to 15 amps. Time characteristics 10 seconds to 120 minutes. Operating principle differential expansion. Description DC over temperature. Application to protect bearings of rotating machines from overheating. Type HM. Rating 100 degrees Celsius. Operating principle volatile liquid. Description over temperature. Application to protect resistance grids from overload. Auto substation control. Type HN. Rating 150 degrees Celsius, 300 degrees Celsius. Operating principle volatile liquid. Description over temperature. Application type generators. Application to protect against excessively high voltage upon sudden clearance of short circuit, used with vibrating type voltage regulator. Type CV. Rating contacts normally closed above 55 volts. Time characteristics inverse. Operating principle induction. Description operates on under voltage. Application to disconnect AC generator in case of fault in winding. Differential protection. Type CA. Rating 5 amps. Time characteristics instantaneous. Operating principle induction. Description AC current. Application to disconnect AC generator in case of fault in winding. Differential protection. Type LECO. Rating 0.5 to 2.5 amps. Time characteristics inverse with definite minimum. Operating principle induction. Description AC current. Voltamps required to operate 2. Application to limit the power fed into system by generators in small substations. Type CW. Rating 5 amps, 70 and 125 volts, 50 to 300 watts, 100 to 600 watts. Time characteristics inverse. Operating principle induction. Description AC over power. Application to protect 3-wire DC generator against excessive unbalanced current. Type TO. Rating 40 to 80 millivolts. Time characteristics instantaneous. Operating principle armature. Description DC over current. Application type converters. Application to prevent starting of SIN converter on low voltage, automatic substation, type CV, rating, special, time characteristics, inverse, operating principle, induction, description, AC over or under voltage, application, to prevent operation on single phase or on badly unbalanced phases, type CM, rating 2 to 6 amps, time characteristics, inverse with definite minimum, operating principle, induction, description, balanced phase current, type CQ, rating 2 to 6 amps, 60 cycle, time characteristics, inverse with definite minimum, operating principle, induction, description, balanced phase current, volt amps required to operate, 20. Application, to prevent converters from running inverted, reverse DC current, type D, rating 50 millivolts, time characteristics, inverse, operating principle, moving coil, description, DC reverse current, application, to disconnect converter when flashover occurs, type MF, rating 100 amps DC, time characteristics, instantaneous, operating principle, armature, description, DC overcurrent, flash relay, application type, motors, application, to disconnect AC motors upon fall in voltage, type CV, rating, contacts normally closed above 55 volts, 90 volts, 140 volts, 280 volts, time characteristic, inverse, operating principle, induction, description, AC under voltage, application, to disconnect AC motors in case of fault in windings, differential protection, type CA, rating 5 amps, time characteristics, instantaneous, operating principle, induction, description, AC current, application, to disconnect AC motors in case of fault in windings, differential protection, type LECO, rating 0.5 to 2.5 amps, time characteristics, inverse with definite minimum, operating principle, induction, description, AC overcurrent, voltamps required to operate. 2. Application, to prevent AC motors from drawing excess power from line, normal voltage, type CW, rating 5 amps, 70 to 125 volts, 50 to 200 watts, 100 to 600 watts, time characteristics, inverse, operating principle, induction, description, AC reverse power, application, to prevent AC motor from returning over power to line when it is being run by a load, type CW, rating 5 amps, 70 to 125 volts, 50 to 300 watts, 100 to 600 watts, time characteristics, inverse, operating principle, induction, description, AC overpower, application, to prevent polyphase AC motors from operating single phase or with badly unbalanced phases, type CM, rating 2 to 6 amps, time characteristics, inverse with definite minimum, operating principle, induction, description, phase current balance or phase failure, Application to prevent polyphase AC motors from operating single-phase, reverse-phase, or with badly unbalanced phases. Type CQ. Rating 2 to 6 amps. Time characteristics inverse with definite minimum. Operating principle induction. Description: phase current balance or phase failure. Voltamps required to operate 20. Application to prevent starting polyphase induction motors single phase or with reversed phase. Type CP. Rating 110 or 220 volts. Time characteristics inverse. Operating principle induction. Description: reverse phase. Application to disconnect polyphase motors upon phase reversal. Type CP. Rating 110 or 220 volts. Time characteristics inverse. Operating principle induction. Description: reverse phase. Application: transformers. Application to disconnect transformers upon overcurrent, applicable where only low ratio bushing type current transformers are available. Type LECO. Rating 4 to 12 amps. Time characteristics inverse with definite minimum. Operating principle induction. Description: AC overcurrent. Voltamps required to operate 2. Application to disconnect high voltage transformers upon overcurrent, applicable on circuits carrying approximately less than 100 amps. Type CB. Rating 4 to 12 amps. Time characteristics inverse with definite minimum. Operating principle induction. Description: AC overcurrent. Voltamps required to operate 44. Application to disconnect transformers in case of fault in winding. Differential protection. Type CA. Rating 5 to 10 amps. Time characteristics instantaneous. Operating principle induction. Description: AC current. Application to disconnect transformers in case of fault in winding. Differential protection. Type CO. Rating 4 to 12 amps. Time characteristics inverse with definite minimum. Operating principle induction. Description: AC overcurrent. Voltamps required to operate 16. Application to protect windings from overheating. Thermostat. Type HM. Rating 100 degrees Celsius. Operating principle volatile liquid. Description: over temperature. Application to protect windings from overheating. Exploring coil. Type CT. Rating 5 amps. Operating principle induction. Description: over temperature. Application: transmission lines. Application for feeder protection from overcurrent with pilot wire. Type CO. Rating 0.5 to 1.5 amps. Time characteristics inverse with definite minimum. Operating principle induction. Description: AC overcurrent. Voltamps required to operate 16. Application to cut out section of transmission line where SC occurs. Line sectionalizing. Type CO. 4 to 12 amps, 4 to 16 amps. Time characteristics inverse with definite minimum. Operating principle induction. Description: AC over current. Voltamps required to operate: 16. Application: to cut out section of transmission line where SC occurs, line sectionalizing. Type: COA. Rating: 4 to 12 amps. Time characteristics: inverse with definite minimum. Operating principle: induction. Description: type: CO with current indicator. Voltamps required to operate: 16. Application: to cut out short-circuited sections of transmission line, line sectionalizing. Applicable where only low-ratio bushing type current transformers are available. Type: LECO. Rating: 4 to 12 amps. Time characteristics: inverse with definite minimum. Operating principle: induction. Description: AC over current. Voltamps required to operate: 2. Application: to cut out faulty section of high voltage transmission line upon overcurrent. Applicable on circuits carrying less than 100 amps. Type: CB. Rating: 4 to 12 amps. Time characteristics: inverse with definite minimum. Operating principle: induction. Description: AC over current. Voltamps required to operate: 44. Application: to cut out faulty line from group of parallel feeders, differential current. Type: CD. Rating: 3 to 7 amps. Time characteristics: inverse with definite minimum. Operating principle: induction. Description: AC, selective differential current. Voltamps required to operate: 7. Application: to cut out faulty sections of transmission lines. Operates according to distance from fault. Type: CZ. Rating: 70 to 125 volts, 4 to 33 amps. Time characteristics: direct with distance. Operating principle: induction. Description: distance or impedance. Voltamps required to operate: Cur L 5 voltamps, voltage L 16 voltamps. Application: to cut out short-circuited section of transmission line with reverse power flow. Applicable at substation and of feeders. Type: CR. Rating: 4 to 12 amps, 125 volts. Time characteristics: inverse with definite minimum. Operating principle: induction. Description: AC directional current. Voltamps required to operate: current L 17, voltage L 25. Application: to cut out short-circuited section of transmission line with reverse power flow, applicable at substation and of feeders. Type: CRA. Rating: 4 to 12 amps, 125 volts. Time characteristics: inverse with definite minimum. Operating principle: induction. Description: type CR with current indicator. Voltamps required to operate: current L 17, voltage L 25. Application: to cut out short-circuited section of transmission line with reverse power flow, applicable at substation and of feeders. Type: CZ with directional element. Rating: 70 to 125 volts, 4 to 33 amps. Time characteristics: direct with distance. Operating principle: induction. Description: direction plus distance. Voltamps required to operate: current L 7, voltage L 30. Application: to cut out short-circuited section of transmission lines with reverse power flow. Applicable at substation end of feeders where only low-ratio bushing type transformers are available. Type LECR. Rating 4 to 12 amps, 125 volts. Time characteristics: inverse with definite minimum. Operating principle: induction. Description: AC directional current. Volt amps required to operate. Current L2, voltage L25. Application: to cut out grounded section of transmission line sectionalizing. Applicable on systems with neutral grounded through high resistance. Type LECO. Rating 0.5 to 2.5 amps. Time characteristics: inverse with definite minimum. Operating principle: induction. Description: AC overcurrent. Volt amps required to operate. 2. Application: to cut out grounded line from group of parallel feeders. Differential neutral current. Type CD. Rating 0.5 to 1.2 amps. Time characteristics: inverse with definite minimum. Operating principle: induction. Description: AC selective differential current. Volt amps required to operate. 2. Application: to cut out grounded line upon reversal of power flow. Type LECR. Rating 0.5 to 2.5 amps, 125 volts. Time characteristics: inverse with definite minimum. Operating principle: induction. Description: AC directional current. Volt amps required to operate. 2. Application: to disconnect grounded lines on solidly grounded neutral and low resistance grounded neutral systems. Type CZ. Rating 70 and 125 volts, 4 to 33 amps. Time characteristics: direct with distance. Operating principle: induction. Description: distance or impedance. Volt amps required to operate. Current L5, voltage L16. Application: automatic network relay. Sectionalizing low voltage networks. Type CN. Rating 120 volts. Time characteristics: inverse. Operating principle: induction. Description: network relay. Application: auxiliary. Application: to trip breaker with AC current from current transformers. Type BT. Rating 5 amps. Time characteristics: instantaneous. Operating principle: plunger. Description: current transfer. Volt amps required to operate. 28. Application: to control tripping of circuit breaker where heavy current is required. Type 20-C. Rating 125 to 250 volts, 75 to 40 amps. Time characteristics: instantaneous. Operating principle: hinged armature. Description: contactor. Application: to control tripping of circuit breaker where heavy current is required. Type 30-C. Rating 125 to 250 volts, 150 to 75 amps. Time characteristics: instantaneous. Operating principle: hinged armature. Description: contactor. Application: to prevent holding circuit breakers closed on short circuit. Type S1. Rating 125 to 250 volts. Time characteristics instantaneous. Operating principle hinged armature. Description trip free. Application to introduce a definite time delay in switching operations. Type CV. Rating special. Time characteristics inverse. Operating principle induction. Description AC voltage. Application to control time of switching operations. Time delay. Type GK. Rating 110 volts 3 to 40 minutes. Time characteristics definite. Operating principle motor operated. Description long time delay. Application auxiliary multi-contact relays for control circuits for continuous service on AC or DC. Type MC. Rating 8, 12, 16, 25, 32, 50, 62, 110, 130, 250 volts DC. 62, 110, 130, 220, 440 volts AC. Time characteristics instantaneous. Operating principle hinged armature. Description multiple contactor. Voltamps required to operate 2 watts min, 8 watts max, 25 voltamps. Application auxiliary multi-contact relays for control circuits for intermittent service on DC only. Type M. Rating 12, 50, 125, 250 volts DC. Time characteristics instantaneous. Operating principle hinged armature. Description multiple contactor. Voltamps required to operate 2 watts min, 8 watts max, 25 voltamps. Application auxiliary control and interlocking relays for switchboard control and signal work. Instant automatic reset. Type OA. Rating 12, 50, 110, 250 volts DC. Time characteristics instantaneous. Operating principle plunger. Description contact making. Application auxiliary control and interlocking relays for switchboard control and signal work. Hand reset type OL and unlashing coil type OX. Rating 110 to 220 AC, 12, 50, 110, 250 volts DC. Time characteristics instantaneous. Operating principle plunger. Description contact making. Application auxiliary control and interlocking relays for switchboard control and signal work. Holding coil type OS. Rating 12, 50, 110, 250 volts DC. Time characteristics instantaneous. Operating principle plunger. Description contact making. Application banked multi-contactor supervisory control. Type MS. Rating special. Time characteristics definite. Description supervisory group of contacts. Application indicator to indicate when relay has functioned. Type C. Rating 0.1 and 1 amps. Time characteristics instantaneous. Operating principle hinged armature. Description operation indicator. Application frequency relay to actuate an alarm or trip a circuit upon a rise or fall in frequency. Type RF. Rating 110 volts rated frequency. Time characteristics instantaneous. Operating principle plunger. Description: 2 coils with balanced lever. End of Chapter 8. Chapter 9, Part 1 of Silent Sentinels by Westinghouse Electric and Manufacturing Company. This LibriVox recording is in the public domain. Westinghouse Protective and Control Relays, Part 1. 1. Alternating current relays. Type CO overcurrent relay. The protective relay, now having the most universal application, is one that may be used to disconnect circuits or apparatus when the current flowing in the circuits or apparatus exceeds any given value. Such a relay has a wide variety of uses. The most common uses are applications to outgoing feeders, transmission lines, generating and substations, distribution feeders at substations, and to motor and transformer circuits. A relay designed for such a diversity of applications must have very reliable characteristics which will allow a flexible adjustment for operation under all circumstances and conditions. Inverse time characteristics. The CO overcurrent relay embodies characteristics which make it applicable to the widest variety of uses for overcurrent protection. The relay is similar in operation to the OA watt-hour meter. It operates on the induction principle, the contacts being closed by the rotation of a disc. It is necessary to have a certain quantity of current flowing in the relay winding before the disc will begin to rotate. After it once has been started, the speed of rotation is proportional to the current flowing in the winding until such current reaches an excessively high value. This gives the relay an inverse time characteristic, or, in other words, the greater the current flowing in the relay winding, the sooner the relay contacts will close. The design of the relay and the action of the damping magnet are such that the time of action is definite for any given current value. Definite minimum time characteristics. Conditions arise in overcurrent protection which demand that a relay used for such a purpose should never close its contacts instantaneously. Because of the inverse characteristics of the CO relay, it is evident that upon excessive overcurrent, the action of the relay would become almost instantaneous. A small torque compensator is added in the relay winding for the purpose of placing a definite limit to the inverse time characteristic. This compensator becomes saturated at excessively high currents and acts upon the relay in such a way that a definite minimum time must elapse before the contacts will close, regardless of the value of current flowing in the winding. This is termed the definite minimum time characteristic of the relay. Current settings. Conditions very often arise where the current supply used for operating an overcurrent relay varies widely due to different current transformer ratios, different conditions under which the relay is desired to act, and different degrees of sensitivity required in the relay. Such an adjustment of operating current is obtained in the CO relay by varying the number of active turns in the main coil winding. This is accomplished by means of a screw in the terminal block at the top of the relay element. The numbers on this terminal block represent the minimum current which will operate the relay. Time settings. It is also very often desired to vary the time in which the contacts will close when any given amount of current is flowing in the relay winding. This adjustment is accomplished in the CO relay by varying the distance through which the disk must rotate before the contacts are closed. This distance through which the disk must travel is adjusted by means of the scale and hand lever located directly above the disk. The time current curve shown on the nameplate of each relay gives the time required for the contacts to close with different values of current flowing in the relay winding with the time lever set on the number 10 graduation. It will be noted from this curve that 2 seconds is the minimum time in which the relay will close its contacts for any given value of current, regardless of how great it may be. This definite minimum time may be reduced, of course, by placing the time lever on a smaller setting. For instance, if the lever is placed on the number 1 graduation, the action of the relay will be almost instantaneous because the disk has practically no distance through which it must rotate before the contacts are closed. Contact troubles have always been plentiful in relay operation. This source of trouble has been largely eliminated from the CO relay by introducing an auxiliary contactor switch interconnected with the tripping contacts so that it closes the instant the main relay contacts close. This arrangement relieves the relay main contacts from carrying the tripping current and also assures good contact even though barely enough current is flowing in the relay winding to close the main contacts. The action of the contacts responsible for making the tripping circuit is, therefore, made positive, and a tripping current of as high as 30 amperes may be safely handled without fear of contact trouble. Type COA overcurrent relay. In many power plants and substations, the space for mounting instruments and other switchboard apparatus is limited. In such stations, it is often very essential also to have supervision over the current flowing in each circuit leading out from the station. A means of providing this current supervision and also relay protection for each circuit without the necessity of supplying and providing room for mounting both ammeters and relays is provided by the COA relay. This relay consists of the CO relay with the addition of a current indicator which serves to show at all times the value of the current flowing in the circuit. The current indicator consists of a thin copper segment mounted on a separate shaft directly above the main disc of the relay in such a way that it is actuated by the same flux that passes through the relay disc. As the relay winding is connected directly in the circuit to be protected by means of a current transformer, the current indicating element shows at all times the quantity of current flowing in the line. The current indicating element also gives a double protective assurance, inasmuch as any accident which occurs either within or without the relay to prevent the main electromagnet from operating the relay disc will also keep the indicating disc from operating. Low energy type CO relay. Certain relay applications are such that only very little energy is available for operating the relay. This is especially the case on high-voltage lines where low-ratio bushing-type current transformers are the only convenient means for supplying energy for the operation of relays or instruments. A modification of the CO relay has been designed to fit such conditions. This low-energy CO relay requires approximately 2 volt-amperes for tripping. In construction and operation, it is very similar to the standard CO relay, except that the contacts are not closed directly by the action of the disc, but through a train of gears. This train of gears also supplies the definite minimum time characteristics, thus eliminating the torque compensator. Due to the construction of the relay, it is somewhat more sensitive than the other CO relays and is therefore suitable for use on applications requiring great sensitivity. The differential protection of generators is an example of this type of application. Type CR directional relay. All relays dependent on current alone for their operation function when sufficient current is flowing in the winding regardless of the direction of the flow. In protecting transmission lines and in making possible the sectionalizing of such lines on the occurrence of trouble, it is often necessary to have protective relays which will close their contacts only when current is flowing in one certain direction. The CR relay has been developed to fill these requirements. The CR directional relay is a combination of the CO overcurrent relay and a Watt element. The current element is the same as that of the standard CO overcurrent relay and has identical operating characteristics. The Watt element is similar to the CW power relay, except that it operates on a very small percentage of normal voltage. The contacts of the overcurrent element are connected in series with the contacts of the Watt element, and as this element will close its contacts only when the power flows in one direction, the relay as a unit operates only when current is flowing in any given direction. As the relay has all the characteristics of the CO relay, the following conditions must exist before the tripping circuit is completed. 1. Excess current must be flowing. 2. Current must be flowing away from the bus bars or in the direction for which the relay is connected. 3. Current must be flowing for a sufficient length of time. Thus, the directional element may close its contacts upon momentary surges of current in the reverse direction, or the overcurrent element may close its contacts on the flow of excess current in the normal direction, but the tripping circuit is completed only when both elements close their contacts. Low energy type CR directional relay. The low-energy CR directional relay has been developed to be used in the same way as the standard CR relay, except that it is suitable where only a small quantity of energy is available for the operation of the relay. The low-energy characteristic of the relay has been obtained by substituting the low-energy CO overcurrent element for the standard CO overcurrent element. Thus, the low-energy CR relay has overcurrent characteristics similar to those of the low-energy CO relay and directional element characteristics similar to those of the standard CR relay. Type CRA relay. In cases where it is desired to have an indication of the current flowing in the circuit, the COA overcurrent element has been used in the CR relay in place of the standard CO element. This makes a compact, convenient arrangement serving the purpose of an ammeter without adding greatly to the expense of installation or detracting at all from the operating characteristics of the relay. Type CZ impedance distance relay. On large, complicated transmission systems, the method of sectionalizing by means of overcurrent and directional relays is often difficult to apply and sometimes even impossible. This is due to the necessity of employing such a large number of relays that it is impossible to keep the timing sequence within safe limits. At times, it is impossible to secure proper discrimination at all, especially in the case of a complicated loop which is fed at several points, and where the points of feed change with load conditions. The Westinghouse Company has recently developed a relay which overcomes all such difficulties experienced on large and complicated systems. Its application does not supplant that of the standard CO and CR relays, but makes protection possible where otherwise it would be difficult or even impossible. The only requisite is that, with a short at the far end of the line, the impedance drop in the line should be at least 3.0% of the normal voltage. That is, the line must be of sufficient length to give this drop. The CZ relay consists of an overcurrent element and a voltage element. The overcurrent element is similar to that of the CO relay. The special feature of this relay is the construction of the voltage element. The voltage element is so constructed that its action in relation to the closing of the relay contacts depends on the distance the relay is away from the fault. In other words, the voltage element acts in opposition to the overcurrent element, and when the relay is a considerable distance from the fault, the voltage on the element is comparatively high, thus lengthening the time required for the relay to close its contacts. On the other hand, the relays near the fault will have a very low voltage imposed on the voltage element, thus causing the relay to operate in much less time due to less opposition being offered to the action of the overload element by the voltage element. Thus, the relay that is nearest to the fault operates first, and at no time does the time exceed 0.75 to 1.0 second. For some applications, it is necessary to restrain the relay from operating unless the power is flowing in a given direction. To fill such needs, a directional element similar to that of the CR relay is added to the CZ relay. Type CA ratio differential relay. The type CA ratio differential relay is a current-operated induction relay, similar in appearance to the type CO relay. As the name implies, it operates differentially, but it differs from the relays usually used in that the tripping current varies with the load. The current required to trip the relay increases in proportion to the line current instead of remaining constant for all load conditions. This feature of the relay provides against faulty tripping due to a combination of through short circuits and variations of current transformer ratio, and allows the relay to be set for close protection at normal loads. Other methods of differential protection generally act on a difference of two currents, so that a slight difference in current transformer ratios increased by heavy loads or by through short circuits is often sufficient to cause enough circulating current to operate the relay. The CA relay is designed to avoid this trouble and will trip out generators and motors on a trouble circuit as low as 2.5% of the line current without danger of tripping them out on system troubles. For protection of star-delta transformer banks, Scott-connected banks, or in any case where the currents in the circuits to be balanced are unequal, the relay is provided with taps so that balancing auto transformers are unnecessary. A saving in expense and in switchboard space is made possible by the provision of these taps. This relay is less sensitive than that used for generator protection. In order to get the ratio feature of the relay, both of the secondary currents to be balanced as well as the differential current are used in the relay. A field proportional to the sum of the currents reacts with a field proportional to their difference, and the resultant field acts to produce rotation. The quadrature flux is supplied to the upper poles by transformer windings on each of the lower poles. Figure 87 shows schematically the connections of the CA relay for the protection of a generator. The arrows show the relative instantaneous directions of current flow under normal conditions. If the currents supplied by each transformer are equal, there will be no current flow in coil A. If the current transformers supply unequal currents, the difference flows through coil A. The direction of current in coil A with respect to coil B does not affect the tripping direction of the relay. The flux produced by coil B tends to hold the relay open, and that due to coil A tends to trip the relay. As the line currents increase, the torque holding the relay open increases, and more torque and consequently more current is required to close it. The relay for generator protection is provided with a tapped difference coil, winding so that the sensitivity may be varied readily. On the transformer relay, the conditions are very similar except that both the sum coil and the difference coil windings are tapped in order to compensate for the effect of unbalanced currents. The sensitivity cannot be varied on this relay. The energy required to operate the relays, particularly the transformer relay, is very small. This, combined with the fact that the operating current increases in proportion to the line currents, makes the relays very adaptable to conditions requiring the use of bushing-type current transformers. When greater sensitivity is required, as in the case of the generator relay, the burden of the relay is somewhat greater, but under these conditions, the current transformers used are of higher grade and the load is well within the capacity of the current transformers. The relay is very rugged. There are no adjustments to get out of order and no delicate mechanical parts to give trouble. The contacts are set well out in front where they can be seen through the glass cover, and where they are easily accessible for adjustments or repair. All the relays are provided with 2 trip circuits and an operation indicator and contactor switch, as in the CO relay. Type CB overcurrent relays. The cost of the current transformers used with relays often forms a considerable part of the entire cost. Where the current transformers must be connected to high voltage circuits, they must be insulated for the high voltages, and their cost is high. The CB relay has been designed for use on high voltage installations. It is a combination of the CO overcurrent relay and the BT transfer relay with the addition of a special contactor switch. A standard transformer is used without regard to insulation for the high voltage line, and the CO relay element is connected in the usual manner. The CO and BT relays, however, with the current transformer are mounted on a slate base, which is mounted on an insulator. The contactor switch is separate from this assembly and is connected to the BT relay by means of a micarta chain. Thus, the tripping circuit is insulated from the high voltage circuit, which is to be protected. When the CO relay contacts close, they serve to operate the BT transfer relay. This relay, in turn, by means of the micarta chain, closes the tripping circuit contactor switch. The operating characteristics of the CB relay are the same as those of the standard CO relay. Type CD Selective Differential Relay. Balanced current protection is very often desired where two or more similar transmission lines are used to connect two stations or two different points in a system. Balanced current protection on such lines means that each line normally carries approximately the same current, and if this condition does not exist, the line carrying the greater current must be in fault. The CD relay furnishes a simple method of securing such protection. It avoids the necessity for any special apparatus, such as split conductor cable, and as it operates on current alone, potential connections or potential transformers are not required. The relay operates on the induction principle and is in reality two overload elements so located that they act in opposition upon a common disk through a common magnetic circuit. Each element is connected separately to its own current transformer and to corresponding phases of the two lines that are to be protected. These two elements are electrically opposed and under conditions of balanced line load, which will give approximately the same current in each element. The fluxes in the magnetic circuit of the relay are equal and opposite, giving a resultant zero torque in the relay disk. When a fault occurs in either line, however, the current in that line will become greater and the unbalance will cause the relay to operate, tripping out the line in which the greater current is flowing. The CD relay has inverse time characteristics and also a definite minimum time of operation with excessive overcurrent. The inherent characteristics of the relay are such that when one line of a pair is tripped out, double the normal current is required in the other line before it will be tripped out, thus making it possible for one of a pair of protected lines to be open and the other line to carry its load without interference from the relay. Any number of lines may be balanced against one another, but the tripping out of certain lines in a group will necessarily destroy the balance connection between the remaining lines. The CD relay has the same current adjustment and time adjustment as that of the CO relay. The time adjustment is, however, seldom of importance, inasmuch as the relays usually are designed to operate almost instantaneously. Type CW power relay. In many instances, a motor is so connected to its load that under certain conditions, the load may drive the motor, causing it to act as a generator. A mine hoist driven by an induction motor is a good example of such an installation. In such cases, it is sometimes necessary to provide some sort of protection to ensure against having the motor return too much power to the line when it is being driven as a generator. The CW power relay serves this purpose. It is also often used to prevent undesirable or excessive interchange of power between parts of a system, as in the case of a small plant connected in parallel with a larger plant where some means must be provided to prevent the small plant from being subjected to the entire load of the system should the larger plant be suddenly disconnected. The CW relay is essentially a contact-making wattmeter. It operates on the induction principle and is similar to the CO relay, except that it requires both current and potential connections. It closes its contacts in but one direction and only after a predetermined time, when a predetermined quantity of power is flowing in a predetermined direction, which direction may be either the normal or the reverse, according to the way the relay is connected. The relay has a standard time adjustment and also taps for changing the wattage values necessary to trip the relay. Type CV voltage relay. The CV relay is designed for general use when it is desired to have circuits or apparatus protected against voltage changes of any predetermined value. It operates to close a circuit either for the purpose of disconnecting the apparatus or of actuating a signal. The time delay characteristic of the relay is used also in many applications where a timing device is desired. In these applications, the relay is used to close the circuit after a predetermined interval when the relay winding is energized. This relay is similar in appearance to the CO relay and operates on the same principle. The chief difference between the two types is that the CV relay operates on voltage, whereas the CO relay operates on current. The latest design of the CV relay is provided with a voltage adjustment by means of which the operating voltage can be adjusted over a wide range. This adjustment consists of a slide wire resistor connected in the upper pole circuit of the relay. The resistor is provided with a calibrated scale so that the relay can be readily set to close its contacts at the desired voltage value. The time adjustment of the relay is identical with that of the CO relay. One form of the CV relay closes its contacts only when the voltage is raised to the operating point or above, and another form closes its contacts only when the voltage is lowered to the operating point or below that value. These two forms are called overvoltage and undervoltage relays, respectively. A third form is equipped with the front and rear contacts. The front contacts close when the voltage is raised above the operating value, and the rear contacts close when the voltage is lowered somewhat below that point. When a relay having a long time delay is desired, it is possible to supply a CV relay with a geared element similar to that of the low-energy CO relay. With this relay, a time delay of as much as 60 seconds can be obtained. Type CP reverse phase relay. In many motor installations, it is very essential that the direction of rotation of the motor always be in a given direction. This applies particularly to motors used in connection with control equipment or for motors used for operating elevators, pulleys, conveyors, cranes, machine tools, etc. The reversal of phase rotation in a polyphase system caused by the reversal of two wires, although not of frequent occurrence, yet is liable to happen at any time when lines are being changed or repaired. Such a reversal of phase rotation means a reversal in the direction of rotation of all polyphase motors connected to the line. The CP reverse phase relay serves to protect against such occurrences. It operates upon phase reversal or when any one phase of a polyphase circuit opens. In case of a phase reversal, the relay may serve to disconnect the motors from the circuit. However, in case of one phase opening with polyphase motors operating on the system, the relay will not operate until the motors have been stopped, due to the fact that practically normal voltage is maintained on all phases by the motor. The relay will operate, however, as soon as the machines are stopped, thus preventing them from being again started. The CP relay operates on the induction principle and has two windings, each of which is energized from a separate phase. The construction of the moving element is such that the disc is maintained in its normal position with the contacts open by the torque produced by the two windings. In case either winding is de-energized or the direction of current in one winding is reversed, the torque becomes zero or is reversed and the contacts are closed by the reversed torque or the action of a spring. As the relay operates on the induction principle and the closing of the contacts depends on the rotation of the disc, a time delay action is produced when the relay operates on low or unbalanced voltage. This time delay action is a very important characteristic of the relay because it prevents the relay from tripping upon the occurrence of momentary voltage disturbances in the line to which the relay is connected. Type CM phase balance current relay. In installations where polyphase machinery, such as rotary converters and motors, is used, it is necessary to have some protective means available whereby the machine will be disconnected from the source of power in case of an unbalanced condition of the current flowing in the phases, or in case of a phase failure where the apparatus would be compelled to operate on single phase. This protection is necessary because a polyphase machine operating on a system with unbalanced phases or on single phase draws excessive current and may overheat. The CM phase balance current relay is used to prevent such occurrences. The CM relay operates on the induction principle and consists of 4 single-phase current elements mounted in a single case. The 4 elements are mounted in pairs, one pair being in the upper part of the case with its own disc, and the other pair in the lower part of the case with its disc. Each disc carries its own set of contacts, the 2 sets being connected in parallel in order that either disc may close the tripping circuit. The 2 current elements in each pair are mounted on opposite sides of the disc and are so connected that the torque produced by one bucks that produced by the other. Therefore, when balanced conditions exist on the system, there is no movement of the disc, but with an unbalanced or opened phase, the balanced condition of the disc is destroyed and the tripping circuit is closed. The relay has inverse and definite minimum time characteristics, and it gives protection for each phase because all phases are represented in the winding. The value of the unbalanced current necessary to trip the relay may be adjusted by means of current taps as in the CO relay. Type CQ phase balance relay. The CQ relay is designed to protect polyphase motors and rotary converters against running in case of an open phase, the reversal of phases, or in case of a 3-phase unbalance, such as is caused by a single-phase short circuit. This is necessary because operation with any of these conditions existing for considerable time will cause serious overheating. It is generally desirable to have machines disconnected from the line on as small an unbalanced condition as possible, and they should not operate on single-phase currents at all. With machines in isolated locations, however, it is sometimes desirable to have the machines kept on the line running on single-phase or unbalanced current if the load to be carried is not high enough to cause serious overheating or vibration in the machine. The CQ relay has current and time adjustments, which make this operation possible wherever it is desired. The relay operates on the induction principle, the operating element being very similar to that of the CO relay. The winding of this element is so connected that under normal conditions of operation no current is flowing in it. However, with any unbalanced condition, current will flow through the winding operate the element and close the contact, which may either actuate an alarm or disconnect the protected machine from its source of power. The CQ relay has an inverse time characteristic. Its construction is such that it is extremely sensitive to small quantities of unbalanced current. The current necessary for operation may be adjusted, and the time required for the contact to close may also be changed. Its application is practically the same as that of the CM, but it is a much more sensitive and a later designed relay and should be used unless the CM is desired for some good reason. Type RF frequency relay. Sometimes it is desired to have the frequency of a circuit or system maintained at a given value, or to have some means whereby a signal is given if the frequency varies from the given value. The RF frequency relay is designed to take care of such applications and may be used either to disconnect a circuit or to simply actuate a signal when the frequency changes above or below the normal value. The relay consists of two coils operating on a balanced lever. The coils are connected across the same source, one with a reactance and the other with a resistance in series. As long as normal conditions exist, a balance is maintained on the lever and the contacts remain open, but a change in the frequency causes a change in the current flowing in the coil that has the reactance in series, whereas the current flowing in the other and resistance coil remains practically the same. This condition causes an unbalance which closes the contacts and serves to perform the required operation. The relay can be made very sensitive and is adaptable to a variety of applications. Type C operation indicator. In many installations where a number of relays are in service, a circuit breaker may be tripped by one of several protective relays. As each relay affords protection against some special kind of fault in the line, it is highly desirable to know which relay has tripped the breaker in order to be able more easily to locate the trouble. As most protective relays reset automatically as soon as the circuit breaker opens, it is difficult to determine which relay has operated without some auxiliary means. The operation indicator is the small coil serving to attract a semaphore into a visible position when the coil is energized. This operation indicator may be installed within the case of all the standard types of protective relays and is connected in series with the tripping circuit. As soon as the relay closes its contacts, thereby closing the tripping circuit, the operation indicator is energized and attracts the indicator to the operated position. The indicator remains in this position until reset. The hand reset of the indicator is so arranged that it may be actuated without removing the cover of the relay. End of Chapter 9, Part 1. Chapter 9, Part 2 of Silent Sentinels by Westinghouse Electric and Manufacturing Company. This LibriVox recording is in the public domain. Westinghouse Protective and Control Relays. Part 2. Direct Current Relays. Installations where direct current is employed are so few and small in size as compared with the present-day alternating current installations that their importance is sometimes overlooked. It must be remembered that there are still many applications where alternating current cannot be used, or at least where no means have yet been devised for using it instead of direct current. On such installations, therefore, it is important to have dependable relay service as protection against overcurrent, reverse current, and other sources of trouble. Type D overcurrent relay. This type serves to furnish protection against overcurrent in direct current circuits. The relay is of the moving coil type with an electromagnet energized by a voltage winding. The winding on the moving coil is connected across a shunt in series with the line and in this way receives a current proportional to the current flowing in the circuit to be protected. The moving contact is carried by the moving coil and is held open by the action of a spring. The torque produced by current flowing in the coil opposes the action of this spring, and when the current reaches any predetermined value, the opposing action of the spring is overcome and the contacts are closed. The electromagnet field is highly saturated, and thus the action of the relay is unaffected by voltage changes. The overcurrent relay may be adjusted to operate over a range with from 40 to 80 millivolts impressed upon the winding. Type D reverse current relay. Conditions are often such that a reversal in the direction of current flow may prove very disastrous. For example, it requires a very small percentage of normal full load current to cause a rotary converter to run away when running inverted. A slight modification of the D overcurrent relay makes it serve as a highly sensitive reverse current relay applicable for protection against such conditions. The moving coil used in the D reverse current relay is such that approximately 2 millivolts will cause the contacts to close. This tripping value may be adjusted to a smaller amount by changing the relative position of the moving and stationary contacts. By using shunts of different capacities in series with the line to be protected, almost any sensitivity required can be obtained. For example, suppose the relay is set to operate on 1 millivolt drop in a given direction and is connected to a 100 millivolt shunt. It will then trip when approximately 1% of full load current is flowing in the reverse direction. Type TO overcurrent relay. The TO relay serves practically the same purpose as the D overcurrent relay, except that its action is not as sensitive and its construction is such that it can be supplied at a lower price. The relay consists of a 2-pole electromagnet serving to attract a pivoted armature against the pull of a helical spring. The tension of the spring determines the tripping point of the relay. The relay is suitable for use with a 50 millivolt shunt and may be adjusted to close contacts on from 40 to 80 millivolts. Type MF flash relay. The flashing over of commutators on rotary converters has been the source of much trouble in the past, and although the improvement of modern design has eliminated the possibility of such occurrences to some extent, the trouble still exists. The MF relay has been developed for the purpose of instantly disconnecting a machine upon the occurrence of a flash over. The MF relay operates by having an armature attraction close its contacts. The coil serving to attract the armature is connected directly between the frame of the machine and the ground. As flashovers usually occur between insulated circuits and the frame of the machine, this arrangement will give immediately a flow of current to ground through the relay coil, which acts almost instantaneously to disconnect the machine from the line. The action of the MF relay is so fast that with the ordinary flashover, the machine will be disconnected before other protective relays farther back on the system have time to operate, thus cutting out on the machine without disturbing the rest of the system. Its speed also aids in disconnecting the machine before any great damage has been done. Type A Polarity Directional Relay. In many electrochemical processes, a current reversal even of small magnitude is serious, in many cases serious enough to cause considerable damage. Such conditions give reasons for the development of a relay to prevent any reversal of polarity. The Type A polarity directional relay fills the requirements for such protection and is applicable also to other uses where a check on the direction of polarity is desired. The relay consists of a polarized electromagnet serving to attract a soft iron armature. The one pole of the permanent magnet consists of two steel cores upon which are placed the two coils of the relay. The relative action of the current flowing in these coils with respect to the pole of the permanent magnet on the soft armature determines the operation of the relay. Its sensitivity and design are such that the contacts will be closed upon any reversal of polarity of the circuit to which it is connected and upon the fall of the voltage to below 20% of normal. Upon the occurrence of an open circuit in the relay winding itself, action of the relay is assured before any voltage has built up in the reverse direction. Type TV voltage relay. Wherever it is desired to protect direct current circuits against excessive overvoltage or undervoltage, a slight modification to the TO overcurrent relay may be used. The TO overcurrent relay with the coils wound for voltage constitutes the TV voltage relay and is applicable for such voltage protection. 3. Temperature relays. Type HM bearing thermostat relays. Type HM relays are designed for use in protecting the bearings of rotating machinery from the disastrous effects of overheating. With this relay installed, it is unnecessary to have constant supervision of the bearings of rotating machinery. This relay is particularly valuable in automatic substation work. The action of the thermostat is largely mechanical. It consists of the operation of a toggle switch by means of the expansion of a bellows. The thermostat unit consists of a bulb which is to be embedded in the bearing, the connecting tube, and the expansion bellows. As the temperature of the material in which the bulb is embedded rises, the liquid enclosed in the bulb and bellows volatilizes and thus creates a pressure, causing the bellows to expand lengthwise. This expansion serves, in turn, to operate the toggle switch, thereby closing the contacts of the relay. The relay usually is made to operate at 100 degrees, but different thermal elements having the temperature of operation 70 degrees, 90 degrees, or 100 degrees centigrade may be supplied. Type HN grid thermostat. A slight modification of the HM thermostat is used for the protection of grid resistors from damage due to overload or to sustain short circuits on the system. The construction of this relay is largely the same as the HM, with the exception of the manner of resetting. This HN relay resets automatically, whereas the HM relay has to be reset by hand. The thermal element supplied with the HN relay is also somewhat different, giving operation at either 150 degrees centigrade or 300 degrees centigrade. Type CT temperature relay. The problem of protecting electrical apparatus against overtemperature presents many difficulties. The object in any such protective apparatus is to allow the protected machine to remain in service as long as it is safe to do so, and yet to disconnect it from the source of power as soon as the temperature becomes unsafe for further operation. In order to obtain the most efficient protection, a relay used for this purpose must take into consideration the ambient temperature, the speed with which the windings of the apparatus heat up when subjected to overload, and the conditions existing when the temperature of the machine becomes dangerously high. The CT temperature relay is applicable on alternating current circuits where the apparatus is so arranged that exploring coils can be installed in the windings. It operates on the Wheatstone bridge principle, the moving part operating on the induction principle. The relay in its appearance is similar to the type CO overcurrent relay. The lower coil is directly connected to a current transformer in one lead of the machine, which is to be protected. The upper coils are connected across the 2 points of the bridge arrangement to which the galvanometer is ordinarily connected. 2 permanent resistance units mounted in the relay case serve for 2 arms of the bridge, while 2 copper exploring coils embedded in the winding of the apparatus to be protected serve for the other 2 arms. The points of the bridge opposite those connected to the upper coils are connected to the current transformer in parallel with the lower coil of the relay. The resistances of the different arms of the bridge are so arranged that at normal operating temperature no current flows through the upper winding of the relay. When the apparatus becomes heated, however, the resistance of the arm formed by the exploring coils changes, thus destroying the balance and causing current to flow through the upper coils of the relay. This produces a torque tending to rotate the discs and to close the contacts. As it is necessary to have a certain quantity of current flowing in both the upper and lower coils of the relay before the disc will rotate to close the contacts, the operation of the relay depends upon 3 conditions. 1. The temperature of the material surrounding the coils must be such as to cause an unbalance sufficient to send current through the upper coils of the relay. 2. The current flowing in the line at that time must be such as to give a sufficient current value in the lower coil of the relay. 3. Heat that has been generated in previous overload, but that has not yet been dissipated, tends to influence the temperature of the exploring coil. Type DT temperature relay. The DT temperature relay is simply a modification of the D overcurrent relay used in connection with a Wheatstone bridge. Its use is similar to that of the CT relay, except that the DT depends altogether on direct current for its operation and does not take into consideration the current flowing at the time when the critical temperature is attained. As in the case of the CT relay, the operating coil replaces the galvanometer connection in the bridge circuit. The 2 opposite points of the bridge are connected across a constant direct current source of voltage. The 2 opposite points of the bridge are connected across a constant direct current source of voltage. 3 arms of the bridge are made up of fixed resistance, while a 4th arm consists of a copper exploring coil embedded in the winding of the apparatus to be protected. The resistance values of the arms of the bridge are so proportioned that when the temperature of the apparatus reaches a safe operating point, there is no appreciable current flowing through the relay moving coil winding. With a low temperature in the winding of the apparatus, current will flow through the relay coil in one direction, and with a high temperature current will flow in the other direction. Thus, with low temperature, contact is made in one direction, while with high temperature, contact is made in the opposite direction. From this, it is evident that the operation of the relay depends solely on the temperature of the windings in the apparatus, leaving out the consideration of the current drawn by the apparatus at the time the critical temperature is reached. This relay, therefore, is applicable wherever a constant source of direct current voltage is available and where the load conditions may be disregarded. Type BA and BD oil-filled thermal relays. Another type of temperature relay which does not require the use of exploring coils embedded in the windings of the apparatus to be protected has been developed. This type depends upon the expansion of a bimetal element. The element has characteristics such that it heats up at the same rate as the windings of the apparatus to be protected. In order to further duplicate the temperature rise of the protected apparatus, the bimetallic element is immersed in oil and the walls of the container are such that the dissipation of heat will be approximately the same as in the case of the apparatus to be protected. The operation of the relay is simple. When the bimetallic element heats to a certain temperature, it expands sufficiently to operate the relay, closing its contacts. The BA relay is suitable for use on alternating current circuits. The BD relay is suitable for use on direct current circuits. It is similar to the BA relay in construction and operation. A cartridge type of relay, which is not oil-filled, is made suitable for either alternating current or direct current application where high precision is unnecessary. The operation of the cartridge-type relay is dependent on the expansion of a bimetallic element in the same way as that of the BA and BD relays, except that precautions are not taken in the relay to have its temperature rise identical in degree with that of the rise in the protected apparatus. 4. Auxiliary relays. In the design of relays, as with any other line of apparatus, it is desirable to adhere to the simplest plan possible. Many relay applications require only a single simple contact arrangement, while others require a more or less complex scheme of interconnected contacts. Rather than complicate the design of any one type of relay to take care of these more complex applications, several different relays are sometimes used to accomplish the purpose desired. In such applications, one relay is usually responsible for starting the sequence of contact operations. This is termed the main or primary relay of the application. The other relays simply serve as contactors, their coil or coils being energized by the action of the primary relay. These relays are termed auxiliary control relays. Type BT transfer relay. In most relay applications where the relay serves to energize the trip coil of a circuit breaker, direct current is used as the source of energy for the trip coil. In some cases, however, it is desired to use alternating current taken from the current transformer to which the relay windings are connected. In such cases, it is necessary to provide some contact arrangement whereby the secondary circuit of the current transformer will be closed at all times and whereby the trip coil of the circuit breaker will be simply inserted in series with the transformer secondary when the relay operates to energize the trip coil. The BT transfer relay is used in connection with the primary protective relays to accomplish this purpose. The main winding of the relay is connected in series with the secondary of the current transformer and the winding of the primary relay and serves to hold the contacts in the normal position. When the primary relay closes its contacts, they short-circuit an auxiliary winding on the BT relay and cause the contacts to operate and thereby cut the trip coil of the breaker into the circuit. The design of the contacts is such that when they are in the normal position, the trip coil of the circuit breaker is mechanically and electrically isolated from the current transformer circuit. The windings of the relay are designed to carry 5 amperes continuously, but during times of short circuit, they may be required to handle as much as 100 or 200 amperes. This can be done satisfactorily for a short period of time. Type MC multi-contact relay. In the application of protective relays, it is often desirable to have several circuits energized at the time the primary relay operates. As most of the standard protective relays close only 1 or 2 circuits when they operate, auxiliary relays are necessary when it is essential to have more than the 2 circuits closed. Another case where an auxiliary relay is needed is when the current required in the control circuit, which is to be closed by the action of the primary relay, is greater than the contacts of the primary relay can safely handle. As in the case of the multiple circuit requirements, auxiliary relays are used to accomplish this purpose, the relay winding being energized by the closure of the primary relay contacts. The MC multiple contact relay fills either of the purposes just described and is used also in many other control installations where a simple multiple contactor is required. Its design is simple and such that it is suitable for operation either on alternating current or direct current circuits and may be allowed to remain energized continuously. The action of the relay is positive and windings may be supplied which are suitable for various values of alternating current or direct current voltage. There are also a variety of contact arrangements which may be supplied. The standard contact arrangements are: first, 4 independent makes; second, 3 makes, 1 break, all independent; third, 2 makes, 2 breaks, all independent; fourth, 1 make, 3 breaks, all independent; fifth, 5 makes, 1 break, all parallel; sixth, 1 independent make, 5 parallel breaks; seventh, 4 parallel and 1 independent makes; eighth, 6 parallel makes. Type M multiple contact relay. The Type M relay is similar to the MC but is simpler. It is suitable for use only on direct current and is intended only for intermittent service. This relay is furnished with either 2, 4, or 6 contacts, the first having the independent and the last 2 the parallel arrangement. Type MS banked multi-contact relay. The MS relay consists of a group of 10 different and distinct contactors similar to the MC assemblies, except that each contactor operates only 2 contacts, or in other words, makes only 2 complete circuits. The 10 units are mounted in a neat case and the complete assembly is used on supervisory control systems wherever it is necessary to insulate the low voltage telephone equipment from the higher voltage power control circuit. The coils of these contactors may be supplied for various values of voltage and the entire group of relays may be applied to various applications wherever it is desirable to have a number of contactors in as compact an arrangement as possible. Type O line of auxiliary relays. The O line of auxiliary relays is intended for miscellaneous switchboard and control use. arrangement usually is such that the auxiliary relays are energized by protective or other primary relays, and they in turn energize or de-energize any desired combination of circuits. They have instantaneous time characteristics. The O relays are so designed that when placed in the normal position and with the main coil de-energized, they make a set of 4 contacts, and when in the operated position, a second set of 4 contacts. The interconnection between the 4 sets of contacts may be changed so that a large number of circuit combinations are obtainable, thus making the relay adaptable to a variety of applications. There are 4 types of the O line of relays classified according to the method of resetting. Type OA. The OA relay has a main operating coil only and resets itself automatically as soon as the excitation is removed from the main coil. Type OL. The OL relay has only the main coil, but it has a latching mechanism which latches the contacts in the operated position as soon as the coil has been energized, and holds them until the latch mechanism is tripped by hand. Type OS. The OS relay is equipped with a main coil to operate the relay and also an auxiliary coil which serves, when energized, to hold the contacts in the operated position after the main coil has been de-energized. This type of relay resets automatically if the holding coil is not energized, and otherwise resets when the holding coil is de-energized. Type OX. The OX relay is equipped with a main coil and also an auxiliary coil which is located similarly to that of the OS relay. It has the latching mechanism so arranged that when the relay operates, the contacts are locked in the energized position until the latch is tripped either by means of energizing the auxiliary coil or by hand. Coils which are suitable for operation on various alternating current and direct current voltages may be supplied for the various types of relays. On account of vibration, only the latching types are satisfactory on AC. The contacts are of sturdy construction and will carry 10 amperes continuously, or will break 5 amperes at 500 volts satisfactorily. Type GK Long Time Limit Relay. It often is desirable to introduce a time interval of considerable length between control switch operation, mechanical operation, or factory processes where a series of operations occur in sequence. A specific example of such application is in the case of automatic railway substations, where various operations must be correctly timed. The GK relay is used for this purpose. It consists of a small motor driving a contact assembly through a train of gears. The contacts of this relay are carried on a drum connected to a worm gear. This worm gear is engaged with the driving gear by an electromagnet, either simultaneously with the starting of the motor or at a certain definite interval after the motor has been started. The GK relays may be supplied with a time limit as high as 40 minutes. Relays whose time can be adjusted to from 1 to 10 minutes can be supplied on special orders. Type JM Group Annunciator. Many features in electric service stations require operation indicators. To satisfy this need, the Westinghouse company has developed the Type JM Group Annunciator, which comprises a group of 12 operation indicators assembled in a glass cover case similar to that of the Type MC relay. The 12 indicators are mounted in 4 rows of 3 each and are all connected in parallel. That is, each has one terminal stud for one side of the line, and all the indicators are connected to a 13th stud, which goes on the other side of the line. The indicators of this annunciator are similar in appearance to the Type C operation indicators described elsewhere in this book, but they differ somewhat from these in construction. The target, which is made of non-magnetic material, is latched in place behind the front plate. When the indicator coil is energized, the latch is pulled back, allowing the operating spring to pull the target into view. All indicators can be seen readily through the glass cover of the relay. They are reset without removing the relay cover by pulling a small knob which protrudes from the right side front view of the relay case. There is a separate reset knob for each roll of indicators, or 4 for the relay. Portable phase indicator for use in making relay connections. In order to obtain correct operation when connecting a relay, which requires both current and voltage connections to a polyphase circuit, it is necessary to select the current and voltage having the proper phase relation to each other. One of the most convenient methods of checking such relay connections is to use a Westinghouse phase indicator. The phase indicator is a portable instrument built on the same principle as is a power factor meter. However, the phase indicator is calibrated to indicate degrees from 0 to 360 instead of power factor percentages. It readily shows the exact phase relation between any current and voltage to which it may be connected. The phase indicator can also be used to check the phase relation between 2 or more currents. An example of such an application is the checking of relay connections for differential protection. To select the 2 current transformers, the secondaries of which should be connected together, it is necessary only to select some voltage for use as a reference, and then to measure the phase relation of the different currents with respect to this reference voltage. End of Chapter 9, Part 2. Chapter 10 of Silent Sentinels by Westinghouse Electric and Manufacturing Company. This LibriVox recording is in the public domain. Instrument transformers. Instrument transformers are used for 2 reasons. First, to protect station operators from contact with high voltage circuits, and second, to permit the use of instruments with a reasonable amount of insulation and a reasonable current carrying capacity. The function of instrument transformers is to deliver to the instruments a current or voltage which shall be always proportional to the primary current or voltage, and which shall not exceed a safe potential above ground. Generally, the secondary of a voltage transformer is designed for about 115 volts and the secondary of a current transformer for 5 amperes, and both these secondary circuits are grounded, together with the cases of the relays, instruments, or meters to which they are connected. Types and ratings. There are 2 general classes of instrument transformers, dry and oil insulated. Dry type voltage transformers are listed for primary voltages up to the 6,900 volt class, and the oil insulated type up to the 66,000 volt class. Current transformers are listed for primary currents up to 10,000 amperes. For voltage classes up to 23,000 volts, the dry type of current transformer is used, and for the higher voltages, the oil-insulated type. The demand for transformers of higher ratings than those given is so small that they are not listed, although they can be built on special order. Oil is used in oil-insulated instrument transformers, chiefly for its insulating properties. It is extremely important, therefore, that it be of the proper quality and that it be kept free from dirt and moisture. Polarity. In connecting instrument transformers to watt meters, watt-hour meters, power factor meters, etc., it is necessary to know the relative instantaneous direction of currents in the leads. For this reason, one primary and one secondary lead of each Westinghouse transformer are marked with a white polarity marker. The relation of the marked leads is such that the instantaneous direction of the current in them is the same, that is, toward the transformer in the marked primary lead and from the transformer in the marked secondary lead, or vice versa. This marking of the leads is carefully checked by a polarity test. Grounding of secondary. All instrument transformers should be grounded on the secondary side as an extra precaution against danger from the high voltage in case the insulation should be punctured by lightning or other abnormal stresses. In polyphase groups, any point of the secondary may be grounded, but it is preferable to use a neutral point or a common wire between two transformers. Insulation. The insulation of instrument transformers protects the meters and control apparatus as well as the power station operators from the high voltage circuits. It is highly important, therefore, that it be able to withstand the strains of service. For this reason, the insulation of Westinghouse instrument transformers is designed with special care. Dry-type transformer coils are impregnated with a compound impervious to moisture. Coils for oil-insulated transformers are dipped in varnish or impregnated to seal them against moisture. Insulation tests. The insulation tests conform to the standardization rules of the American Institute of Electrical Engineers. Voltage transformers. Uses. Voltage transformers are used with voltmeters, watt-hour meters, power factor meters, frequency meters, synchronoscopes and synchronizing apparatus, protective and regulating relays, and the no-voltage and over-voltage trip coils of automatic circuit breakers. One transformer can be used for a number of instruments at the same time if the total current taken by the instruments does not exceed that for which the transformer is designed and compensated. Voltage transformers have a capacity of 200 volt amperes, but are compensated to give correct ratio at 40 volt amperes, as this is the average load demanded by a voltage transformer. Special transformers may be compensated for a correct ratio at any load up to the full capacity of 200 volt amperes. The standard secondary voltage is 115 volts nominal to suit standard instruments. Instrument transformers with special secondary voltages can be made if necessary. Principle of operation. The voltage transformer is, in principle, an ordinary constant potential transformer, especially designed for close regulation, so that the secondary voltage under any condition will be as nearly as possible a fixed percentage of the primary voltage. The secondary voltage can never be exactly proportional to the primary voltage, or exactly opposite in phase to the primary voltage on account of the losses in the transformer and the magnetic leakage between coils. There are two classes of errors inherent in voltage transformers: ratio error and phase angle error. The part of these errors due to the exciting current is constant for any particular voltage. It can be reduced to a minimum by choosing the best quality of iron and working it at a low magnetic density. The part of the errors due to the load current varies directly with the load and can be minimized by making the resistance and reactance of the windings very low. Current transformers. General. The current transformer is a special development of the transformer principle. The object is to maintain a constant ratio between the currents in the primary and secondary windings instead of a constant ratio between the voltages, which is the usual requirement. Uses. Current transformers are used with ammeters, wattmeters, power factor meters, watt-hour meters, compensators, protective and regulating relays, and the trip coils of circuit breakers. One current transformer can be used to operate several instruments, provided that the combined burden does not exceed that for which the transformer is designed and compensated. Principle of operation. The ordinary voltage transformer or distribution transformer is connected across the line, and the magnetic flux in the core depends upon the primary voltage. For a given voltage, the flux is, therefore, fixed, while a current in the winding rises and falls as the load of the secondary winding changes. The current transformer is connected directly in series with the line. For a fixed number of instruments in the secondary, which is the usual condition, a rise or fall in the line current requires a corresponding rise or fall in the secondary voltage to force the secondary current through the impedance of the meter load. The magnetic flux in the iron, which supplies this voltage, thus follows the rise and fall of the primary or line current. In any transformer, the primary ampere turns may be considered as made up of two parts: one small element, which supplies the magnetizing and core loss current, and another element which supplies the working current. The working current ampere turns are always exactly equal to the secondary ampere turns. End of chapter 10. End of Silent Sentinels by Westinghouse Electric and Manufacturing Company.